Okay. Okay, so now, yes. Okay, so it is audible as well as visible. Okay. Now, in the previous marathon, actually, we covered NCRT solved example, exercise question, and we have taken questions from the exemplar also. That file in which we had the face examination, 180 questions from the 180, okay. If you have that file, you have to, okay, at least you can revise those, okay. One was the examination in which 180 questions were there. They were taken, okay, they were taken from the NCRT or NCRT exemplar. As well as in the class, that PPT was there, in which I took some important questions from the exercise also, solved example covered, as well as your exemplar also covered. So you can have that, okay, one time revision of that. So today we'll go for the quick revision, whatever the important area in each topic, and from those topics, what questions they can ask. That will be the target for today. So sit tight, and one thing is there that we will be having okay 3 hour, and in this one we have to mainly cover the, in the 12th class, modern physics is there. Then optics and ray optics. These are the, okay, one is the modern physics, and then one is the your optics part. Modern physics itself is always important, and easier also, means if you listen this class carefully, probably you will be able to do the questions of modern physics. Roughly around 7 questions you can expect from there. So if 7 and plus your optics, we can say 4, so it will be the almost 11 to 12 questions. This one I'm saying the minimum. It can be more, okay? Because generally we take that 8 questions from there, but okay, I'm taking the minimum side, okay? That minimum this much will be there, okay? It will be 100% more, okay? Okay, you can see if I take the maximum one, then it can go up to 14, 15. So first of all, in the modern physics, we'll go with the your photoelectric effect. Quite basic, already you have done in the physics and chemistry. It will be useful in the physics also, and in the chemistry also. They can ask questions of photoelectric effect. This is the good thing, that photoelectric effect, de Broglie as well as atom. That is common with the physics or chemistry. Means questions will be coming in the, in physics. You will see that yes, questions are there, as well as they can ask questions even in the chemistry. So you can say that weight is slightly increases. Now first of all, we have in this one that your about the photon, you need to remember in the, okay, that first of all you need to know that energy of each photon is directly proportional to its frequency. Means E equal to, we can write here h nu, where h is going to be your constant, Planck constant. Here dimension of Planck constant you have to know in this one, okay. 6.6 into 10 power minus 34. You can write this formula as like this also, E equal to hc by lambda. Means photon is nothing but just packet of energy, okay, and here in this one, each packet is going to have that h nu energy, okay, or we can say hc by lambda. Remember that for the photon we are going to use this formula, either this one you can use, either this one. If I put the values of this one hc, then we are getting 12400 divided by lambda. This lambda will be in the angstrom, and if you use that, now we can say this energy will be in the, means I can write this way, that here E equal to, we can write 12400 divided by lambda. This wavelength how to be in the angstrom, and this energy will be in the electron volt, okay. Mainly we are going to use this one. Now this formula we'll use here, we'll use, okay, in the multiple chapters, whenever we are talking about the photon, you have to use this 12400, okay. Now in the EM wave also they can use this one. They will say the energy is this, energy is like, okay, if I say, okay, with respect to EM wave, I'm saying, okay, in the EM wave, they will be asking the question, because these questions are now more probable, because the spectrum is specified in the syllabus. Now we can write here that they will say that 15 kilo electron volt. If energy equal to 15 kilo electron volt, then you have to find which spectrum is this. Okay, means this radiation belongs to which spectrum. So now you can see that energy 15 kilo electron volt. Directly also you can guess this is the so much energy, huge energy means this how to be from the X-ray. Otherwise you need to calculate this wavelength. Okay, so we can say lambda will be equal to in this one 12400 divide by, we can write here 15 kilo electron volt means 10 power, okay, 3. If you say roughly, okay, you can calculate, but I'm not calculating. Roughly comes around 1 angstrom, okay, slightly less than 1 angstrom. Means this will be in the zone of X-ray, okay. So spectrum you need to remember here. So we can see yes, this formula we are going to, okay, use for the whenever photon will be there. I will be taking question with the de Broglie, in which also you have to use simple formula Hc by lambda or 12400 by lambda. In the photoelectric effect, we'll see the question like this. I will okay, see the radiation of wavelength. Okay, another question if I take, they will say radiation of wavelength. Okay, your 4000 angstrom incident, okay, 4000 angstrom incident, I will take in the next page, okay, that they are saying here that radiation, this question, okay, radiation of 4000 angstrom, or let me take 3000 angstrom incident, okay, on a surface with threshold wavelength, I am writing with lambda not equal to 4000 angstrom. Okay, like this question they can say that radiation of 3000 angstrom incident on a surface with lambda not means threshold wavelength is 4000 angstrom. Now they are asking, okay, find, okay, now they can ask find number 1 E, number 2 they can ask okay, what are the work function, number 3 they can ask what are the K max, number 4 they can ask what are the stopping potential. I am going to ask all these things. Okay, so now you can see, because a straightforward question coming, you can use the formula, okay, of photoelectric effect here. What is the formula of photoelectric effect? You know, formula is simple here. We know that is the E equal to in this one phi plus K max. Okay, everyone knows this formula. I'm writing directly. Okay, we cannot go as the like main class. So equal to phi plus K maximum is the formula, one and only one formula in the photoelectric effect. Okay, so out of this formula, whatever is possible, everything I'm asking in this particular question. Now we can say first they are asking E. So you can say E, we have to calculate E is the energy of incident ray. This is the energy of the, okay, incident radiation. This one is the work function. So we can say E, we will calculate using the formula 12400 divided by this your 3000, because incident radiation is having here 3000. Now we can write here 20, you can cancel, okay, and you will get here roughly 4.1 electron volt, close to 4.1 electron volt. Little bit approximation you can take all the time. Okay, so this is the 4.1 incident radiation, 4.1 electron volt. Now we can see we need to find the work function. Work function you will get from the threshold wavelength. So we can say work function phi. Some people say this one is the W not also, whatever you say. So we can say phi will be equal to in this one again 12400 divided by your 4000 you can write, and from here you can say my work function will be equal to 3.1 electron volt. Okay, so they might ask simple that radiation given, then energy, what are the energy wavelength given, they can ask threshold wavelength given, they can ask what are the work function. Now we got first one, we got second one. They are asking what will be the K maximum. You can just put the values here equal to, that is the your 4.1 equal to, you can say here 3.1 and plus this is the your K maximum. Here you got K maximum equal to, okay, this will be the 1 electron volt. I'll be taking less examples and using the same example I will try to cover so many things. Means that will be the, okay, meaning of the marathon also, one example and which covers most of the things, so that using the single means using the 3-4 question you can get a lot of things. So now we got here in this one K maximum 1 electron volt. Sometimes they will, okay, there, so we got the K maximum here. Let's do the stopping potential. Maximum electron is having 1 electron volt. Okay, all the electron don't have 1 electron volt. Sometimes they will ask kinetic energy of the ejected electron. Okay, if I ask here in this one, number 5, K of ejected electrons, then we can write here K of ejected electrons. All electrons don't have same kinetic energy. Okay, kinetic energy of ejected electrons will be always 0 to K max. This thing you have to keep in the mind, that all electrons don't eject with the same kinetic energy. Some are loosely bounded, some are tightly bounded, some energy losses will be there. Based on the probability, we can say electrons will be having energy from 0 to K maximum. Some electrons just ejected with very less energy, we can say 0, and some are ejected with the maximum energy. This equation gives you information of the maximum energy. So we can say K of ejected electron always from 0 to K maximum will be there. So you can say this is going to be 0 to 1 electron volt. Okay, means here in this case minimum energy will be 0, maximum energy is going to be your 1 electron volt. Minimum is 0, maximum is going to be 1 electron volt. Okay, stopping potential we decide always from the maximum kinetic energy. Stopping potential is the basically here your potential applied at anode, negative, potential applied and negative potential applied at anode with respect to cathode. It how to be with respect to cathode. Remember this definition. Negative potential applied at minimum negative potential, least negative potential applied at anode with respect to cathode. This line with respect to cathode we have to take all the time. To stop maximum kinetic energy electron, your target will be always to stop the maximum K electron. So we can say here maximum K electron means in this case stopping potential we can write here minus 1 volt. To stop this one, minimum is the minus 1 needed. Suppose K maximum you get here 2, then here you how to write what? Minus 2. If this is the 5 electron volt, you have to write here minus 5. Okay, so I hope this question is clear. Yes, so we got here in the 3000 angstrom radiation given, then threshold wavelength was given. So E phi K maximum stopping potential and kinetic energy of ejected electron will be your 0 to K maximum always. Okay, now I will be adding one more question here from the de Broglie. Okay, because they can ask questions from the any of the questions. So I will be taking the next page here. I hope this page is very clear to you. Okay, only single relation you have to keep in the mind. Okay, questions like this, if they have given the direct data is the very easy. We can put stopping potential always decided by the maximum kinetic energy electron. However, all electron don't have the same energy. Their energy ranging from 0 to 1 electron volt. Okay, now if I say in the next one here, same question, find. Question continued. This is your fifth part. Now we can write here sixth one. Find dBW, de Broglie wavelength of ejected electrons. Ejected electrons, de Broglie wavelength also you have to find. This is the question where most of the people do the mistake. Now we know our kinetic energy. If you see, K is actually if I write here 0 to 1 electron volt means 0 to 1 electron volt. This part, this is the minimum, this is the maximum. Kinetic energy ranging from minimum to maximum. In this question, this is the 0 to 1 electron volt. Now if you have to find the de Broglie wavelength, for this formula you have here, the 12.27 divided by root V. This is the formula for electron, and mostly they are talking about the electron. And as of now, we have electron here. So I will talk about the electron. 12.27 by root V. Here, this wavelength will be in the angstrom. 12.27 by root V. Now, if I talk about the potential, then we can say this will be the 0 volt to, we can say 1 volt. Now, if this V is the minimum, if V minimum, then lambda is going to be the maximum. V minimum, it is going to maximum is at, if I say 0 volt, then you can say, sir, lambda tends to, in this case, lambda tends to infinite. When this is the minimum value, then lambda tends to infinite value. Lambda will be having the maximum value. So lambda can be approaching towards the infinity. And if I say at 1 volt, which is the maximum, if I take the maximum, then we can say in this case, lambda will be taking the your some minimum value. That minimum value we can calculate from here, 12.27 divided by root 1, which is the, okay, your root 1. So we can say this becomes 12.27 angstrom, okay, 12.27 angstrom. But you know, this is the minimum value. So you got here in this one that your wavelength is, cardiac energy is ranging from 0 to 1, 0 to, okay, means minimum to maximum, and your de Broglie wavelength, because, okay, we can say when 0 to 1 electron volt means potential we can read 0 to 1 volt here, and lambda 12.27 by root V here. When V is minimum value, then lambda is approaching towards its maximum value. Electrons, okay, eject electrons. Then which of the following cannot be used for photoelectric effect? Which of the following cannot be used for the photoelectric effect? They're saying red color is just able to eject. And if red color is just able to eject, whenever they use this word just able to eject, means that is the your threshold, okay, that will be the your okay, threshold here. So we can write in this one, red color, okay, is the threshold here, okay, means this one is the actually your okay, I can say, okay, this one is the, okay, your threshold wavelength, threshold color. Anything more than this cannot be used. Anything okay, here, because this side more energy, this side lesser energy, okay, so more energy can be used, less energy cannot be used. If I write the your options here like this, okay, they will be writing the X-ray, they will write your UV, they will write okay, blue light, they will write here in this one your IR, okay. You know that IR cannot be used because IR is having the lesser energy, okay. If IR, then okay, will be having less energy than this red, we can say we cannot use. Like this we can say. Sometimes they can ask which one can be used, we can say more energy can be used, less energy cannot be used. This is the one type of question which they can ask. Now again I will add here. Then comes okay, number of photon, one important topic here. They can say number of photons from a particular source, okay. So number of photons always you will calculate using this formula, 5 into 10 power 24 p lambda. You have to keep this formula in the mind, 5 into 10 power 24 p lambda. Here question I can write like this, okay, 5 into 10 power 24 p lambda. First of all, you have to remember that number of photons given by 5 into 10 power 24 lambda. If I write the question, they will say that any type of source they can say bulb is there, they can say one dipole antenna is there, okay, they can say this is the your okay, point source, okay, like this, they can say like this is the dipole antenna, okay. Just to confuse you, dipole antenna given, anything given, always you have to use the same formula. They will say power of the source is 5 milliwatt. Listen, whenever they write this small m, one is the capital M, one is the small m. If capital M means that is the mega 10 power 6, and if small m written, that is the your milli. So here this is the small m. So see clearly what is written, okay, milli or mega. Means you can say 5 into 10 power minus 3 in this one. Then they are saying that wavelength is, suppose your 5000 angstrom are taken, they will give you whatever they want, okay. And let me take this one in the nanometer, okay. So 500 nanometer, because we are doing this mistake, I have to say this conversion also here. 10 angstrom is always equal to your 1 nanometer, okay. 10 angstrom equal to 1 nanometer you have to keep. So here given 500 nanometer, you can say this will be equal to 5000 angstrom, okay, this one, clear, 5000 angstrom, okay. Once you got these values, then you have to use the formula for this one, n equal to 5 into 10 power 24 p lambda. Can you put the things here? Okay. So this is the number of photons. Now here I'm saying, just to confuse, they can say dipole antenna, they can say your point source, or anything. We have to just use this formula. Okay. Now comes here some graph based questions. You know that if more photon incident, then more electrons will be ejected. So we can say number of photons, number of photons will be directly proportional to number of electrons. This will be directly proportional to your current, and you can say number of photons is proportional to the intensity. Okay, so from here you got that yes, intensity will be directly proportional to your photo current. And in this one we can write this graph. You will keep in the mind, this is the your I, and here we can write here I. This graph is going to be a straight line, but this relation is only valid if ejection happening. Okay, if ejection happening means nu is greater or than nu not. We talk about these things only when there is the ejection. Ejection means your frequency how to be more than the threshold frequency. Okay, frequency should be more than the threshold frequency, means greater than or equal to the threshold frequency here. Okay, so this is the first graph that you will keep in the mind. Then we can say some graphs are there from the experiments like this, that we got here. Okay, like this one is there. We can say this is known as your saturation current here, and at this point indicates the your stopping potential. Okay, this one indicates the stopping potential. This is the graph between I and V. Okay, so this is the first graph. This current will be saturated. When current will be saturated, you know that electrons are having 0 to maximum. So when you don't apply any battery, zero potential applied, then all the electron don't reach, only highly energetic electron reach. Then you will apply battery that some potential, positive potential. This positive potential will attract, like this indicates here. When you have applied here nothing, zero potential, then current is there. But if you apply here +1, +2, +3, +4, then current keep on increasing, then it becomes maximum. Okay, because when all electrons reaching, then this potential cannot pull out electrons. Okay, so we can say current becomes maximum, means saturates. If you apply some negative potential like -1, -2, -3, okay, then what will happen, that number of electrons reaching the anode will decrease, and at some particular potential, even the highly energetic electron will be having so strong repulsion that this even cannot reach the anode. So we can say current in the circuit becomes zero. That potential, that negative potential, we can say is known as your stopping potential here. Okay, so this is the graph that you will remember. This represents the your stopping potential, and your stopping potential is basically related with the kinetic energy, and your Ke always depends on Ke. If you say no, then you can say this will be the h nu minus phi. So Ke depends on the your nu as well as phi. For a material, I can say phi to be constant. If they're asking theoretical question, then your Ke of electron depends, then we can say depends on the work function as well as threshold frequency. But for a surface work function to be constant, so I can say that this point will indicate here your frequency also. More Sp, more kinetic energy, more frequency, because for a surface work function will be constant here. Okay, so I will take the next graph here like this. Now, in this one, they are saying here that we got this graph, and they are saying this is the new one and this is the new two. They're asking which is having more value. You can clearly say that this one is having more value. New one is greater than new two. Why new one is greater than new two? Because this is having like stopping potential. This is the -10 volt. This is the -20 volt, -5. Okay, -8. So this is the 5 electron volt, this is the 8 electron volt. Here energy more, that's why frequency will be more. New one is greater than new 2 in this one. I will take next question now. They can say sometimes like this, that we got here same source is there. Okay, and now in this one here, this is the I. They are asking this one is having intensity I1, this intensity is I2. If these 2 points are matching, then we can say your frequency is going to be same for both. Okay, means new one and new two both are going to be same. If this is the your new one, okay, and this is the nu2, then we can say here, okay, nu1 equal to nu2, both matching here. Now I1 and I2, you can clearly see that current more intensity more, so I1 is greater than I2. You will remember this thing, that if intensity is more, okay, means current is more than intensity, how to be more here, okay. Now then coming for the next graph here, this can be the mixed graph, okay, because they can ask question from the equation, either question from the graph. So we can say it is like this, and here given this way. Now in this one we can write here, this is the your matching here, so nu1, this is the nu2, this is the nu3. You can clearly see that nu3 is greater than here nu1 equal to nu2, but in this one you can write here that this is the suppose I3, this will be the I2, okay, so you can say I3 is equal to I2, and this is the I1, means I3 equal to I2, but this one is greater than I1, okay. Yes, if they are going to ask, okay, common question. Now I will take next graph here. They can say that in this one that we need graph of K equal to, here in this one if I write, you know that H nu minus phi, because you know kinetic energy equal to, here in this one we can write K becomes your E minus phi. So you can compare with this one, y equal to mx plus c. Now we can write mx plus c. So your slope here in this one, you can say slope, okay. I'm taking this one here K, and here we can take the your frequency. So we can write here slope is equal to Planck constant, and the C is equal, okay, representing here work function. So the C is downside, so we can write a negative side, and then okay we can write like this, okay, and graph starts like this. Here I am putting dot dot dot, okay. They can put solid line or dot dot dot, because we know this is the minimum frequency after which ejection will be there. Lesser than this ejection not there. They are putting solid line, does not matter, okay, but nu naught is the minimum frequency at which ejection will be there, okay, means beyond this, lesser than this, ejection not possible. Here you will remember that this slope is always same for all, because it is Planck constant, and this thing is equal to your work function phi, okay. So we can say in this one, if they are going to ask for the different material, like this one is there, so you can say whatever material is there, okay, like this is the A, this is the B, this is the C, all will be having same angle. If this is the theta, this will be theta, this will be also theta. Angle is going to be same. Why angle is going to be same? Because you know slope represents here Planck constant, and that is going to be same in the, okay, irrespective of whatever material we are using, it is going to be exactly same. You can say they can ask which will be better for the, okay, like this we can extend here, and then you can say that this will be the phi A, this is the phi B, and this is the phi C. You can clearly write that phi C greater than phi B, and then greater than phi A. So we can say A is okay, suitable or best for photoelectric effect, okay. A is having the lesser work function, so best for the photoelectric effect. Here two questions are hidden. The angles, we can say all the time these angles will be same, and here this is the phi A, phi B, phi C. This is having more work function, this is the most suitable for photoelectric effect here. Clear this one, these graphs. Now we'll go for the next one here. In the K, if they ask na here, because K will be equal to, you can write simply equal to your EV naught also, okay. So only that change will be there, okay, that's here H by E, okay. It simply becomes H by E, okay. Slope only changes H by E. Now we can write next thing here in this one, that K equal to, you know that hc by lambda minus phi. Again you can see here in this one that if lambda increases, kinetic energy will decrease. This one coming from the same E minus phi, because E I can write h nu, either hc by lambda. So you can see in this one, whenever one increases, other decreases, it how to be like the your okay, rectangular, means your hyperbola type, okay. Type I'm saying, okay, I'm not saying hyperbola. So you can see that it how to be, okay. Here we can say K, this is the your lambda, like this, okay. But at somewhere this graph okay, will be stopped, because beyond this, if you say, then ejection will not happen. This how to be, okay, this how to stop at some point. Okay, this is the threshold wavelength, is the maximum wavelength at which ejection will be there. Beyond this, there is no ejection. Okay, this is clear here. Photoelectric effect is completely done, properly done. Okay, now dual nature, already I have taken some questions. Some questions I will take on this one. First of all, you have to remember this formula, that lambda equal to h by p. It will be equal to h by mv. It will be equal to h by root of 2m ke. Okay, 2m k. Okay, if they say in terms of potential, then we can write in terms of potential, it becomes 2m, okay, q delta v. In terms of temperature, if they are saying, then we can write it becomes 2m. Kinetic energy, we can write 3 by 2 kt. 2 you can cancel. So these are all formula written here in terms of temperature, in terms of potential, in terms of kinetic energy. They are asking these graphs, any of the graph, because you can say here that momentum increases, lambda decreases, v increases, lambda decreases, kinetic energy increases, lambda decreases. Okay, your potential increases, lambda decreases, temperature increases, lambda decreases. And once, okay, one increasing, other decreasing graph, you can simply say for all these relation, it will be like this. Okay, simply we can say whenever one increasing, other decreasing, graph is like this. Always remember, everywhere for all the chapter, one increasing, other decreasing graph. Okay, so whatever relation they are going to give you, any of the one of the relation they will give. Previously they have asked also. So anything is given to you, we can say, simply say that graph you have to choose this way. Okay, you have to just identify one increasing, other decreasing graph will be in this format. Okay, both increasing, then yes, we can go for the, okay, a straight line. Okay, we can see, but generally this is there. Okay, now in this one I will take the first question here, and very important also. For electron, already I said, you will remember. Okay, for any particle, okay, you will remember any particle, that is lambda will be equal to h by root 2mk, means its kinetic energy. Okay, for any of the particle, if you have, okay, any particle like electron is there, proton is there, okay, neutron, anything, whatever they are saying, okay, etc. We can write here from this k will be equal to h square by 2m lambda square. Either you can remember this, either this one, that kinetic energy h square by 2m lambda square will be there. Okay, but for photon, okay, for photon, always you have to remember energy is simply equal to hc by lambda. Okay, these two relation you have to keep. A lot of people are doing mistakes in these relation, that for any particle you will use lambda equal to h by root of 2mk, and if photon is there, you have to use hc by lambda. Like I will ask one question on this one, then I will go for a question on these. So first, if I take here, they are saying if photon with wavelength, okay, lambda 1, and proton with wavelength lambda 2, okay, with wavelength lambda 2, okay, had same energy, okay, means they have same energy. Okay, these have same energy. Find lambda 1 by lambda 2, means some relation they will ask. Okay, or lambda 1 by lambda 2 proportional to, in the last examination we ask also. So for photon, if you have, then photon you will always write that energy equal to hc by lambda of 1. So we can say lambda 1 will be equal to hc by e. Okay, hc by e here. Okay, in this one, h and c constants, we can say lambda 1 is proportional to 1 by e. Okay, this one, first of all we can write. Then we can write here in this one that your for, okay, proton or any particle, they can say electron also, you can write here in this one that lambda 2 will be h divided by root of 2me. Okay, h by root of 2me. We can see here lambda 2 is proportional to 1 by root e. I hope we can divide and get the relation. Yes, suppose they are asking this formula only. Sometimes they will ask lambda 1 by lambda 2. Now I'm, okay, putting This way lambda 1 we can write here, it becomes simple hc by E, and this lambda 2 simply your h, and you can take this one here, okay, root of 2m E upside hh you can cancel, and now we can say lambda 1 by lambda 2 will be equal to, in this one, okay, you can see here, okay, your 1 is root E here, so we can write it becomes how much, root of 2m c I can take inside, so 2m c square divided by E, okay. Sometimes they can ask like this, or they can ask the ratio that lambda 1 by lambda 2 proportional to, so lambda 1 by lambda 2 proportional to 1 by root E. So some question like this, they can say same energy, they can say same wavelength, whatever the condition they are going to give you, you will remember that for the photon I will use this one formula, for any other particle, proton, electron, I have to use this formula, okay. Photon always hc by lambda, for other particle h by root of 2m ke, or h by, okay, k means here we can take the E, okay. So ratio based question or any relation, okay, this also you will see somewhere, you will keep this thing in the mind, okay. Fixed question will be there, okay. Now I will take the next question. This question will be, okay, again from your NCERT solved example. In the, they have given that, okay, I will slightly modify, okay, I will include one more here. Proton, deuteron and alpha particle, how, okay, same potential, or okay, particles are accelerated by same potential. They can say same potential, or they can say same energy. Two questions are there, okay. If I say same energy, question becomes slightly simple. I'm saying the same potential, okay, one step more. So one step more or one step less, okay. They are asking ratio of dBW, means lambda proton to the lambda deuteron to the lambda of alpha. You can say now here, formula is simple, h divided by root of 2. Here we'll write for this one mass of proton, charge of proton is E, and then we can write potential is V. For the deuteron we can write h divided by, okay, generally they will talk for 2. I am taking for all three possibility of, okay, whatever, all three together. They will ask only for 2 in the examination probably. So we can say this becomes here, okay, 2. Mass of the deuteron will be 2 mp, charge is E and V, okay. Formula I am using this, okay, this formula we are using here that I have told you, 2m, okay, qv, but because charge is your E, so 2m qv formula I am using here. Now we can write in this one, for the alpha particle we can write h divided by root of 2. Mass of alpha particle is 4 mp, its charge is 2e, but potential is same for all. So you can say now h we can cancel here. MPeV, 2 MPeV, here 2 MPeV, and here also 2 MPeV, okay. So you can say this becomes 1. Here it will be 1 by root 2, and this one we can say in the 8 here, so 1 by 2 root 2, we can write this thing as 2 root 2, and here we can write 2, and this is the one simplest ratio. They will ask any 2, you should be able to solve, okay, for any 2. I hope this is clear here. And remember what they have given, just don't remember blindly, okay, that same potential or same energy. Next I will take, suppose, okay, one question for the same energy, okay, so that you will remember the difference here, okay. So I will say proton and alpha particle have same energy, okay, same energy, then ratio of dBW. Now we can say formula first of all, lambda equal to h by root of 2me or 2m ke, whatever you can see. This is the formula, okay. They have same energy, means in this case you can write here h constant, E constant, 2 constant. It means only m is there, means lambda 1 by lambda 2 or lambda proton divided by lambda of alpha will be equal to basically here root of mass of alpha divided by mass of proton, okay. So in this one only we are taking the mass, they have given same energy. So read same energy given or same potential given. Then we can write here mass of alpha which is the 4 MP divided by, we can, this is the MP, and we can say now answer is 2 by 1. Okay, I hope we can do these questions. Possible? We are taking those where, okay, people are going to do a mistake and which are the most likely also. Same potential, very important, and then same energy here. Okay, already electron I have taken, electron 12.27 by root V, so I'm not taking more questions on that one. Okay, photon and particle relation taken. This photon and particle relation is very, very important. So if I say in the de Broglie, one question this, okay, keep in the mind, similar to this, they might change the particles, but have the same energy. Here, this is the same potential in this one. And then we have seen here relation of the photon and particle, because whenever they are asking the question on this relation for the photon and particle relation, mistake happens. So remember, for the photon we'll use hc by lambda. For any particle, proton, electron that is there, we will use h by root of 2me. And okay, these are the some basic things in this one. Okay, now so your de Broglie is finished here. Now we'll go for the your atom. Okay, atomic structure and common for in the physics as well as chemistry. Your first model Dalton failed, Thomson failed because Thomson just said electrons are just filled. Now we know electrons are different energy levels. Then Rutherford come. Rutherford, you have to remember some basic things in the, okay, your Rutherford. One thing I will say here, that whenever, okay, these are the your, okay, nuclei here, we are sending these alpha particles. Okay, this is the alpha particle scattering, one is the electron scattering. Okay, to estimate the radius in the proper way, we will prefer the electron scattering if used. Okay, but he used the alpha scattering. So saying about this one, now you can see this alpha particle keep on going, and at some distance it will stop. Okay, somewhere due to the repulsion that will be known as your distance of closest approach. So here you need to remember this one, distance of closest approach. At this one, what happens, its whole Ke is converted to the potential energy of the system. Kinetic energy of the alpha particle, okay, whatever due to the repulsion, okay, this Ke will be converted to the your potential energy of the system. We can write here K will be equal to, in this case, potential energy we can write K Q1 Q2. So K Q1 is your ZE, this one is the 2E divided by, we can write here in this one your R naught. So from here we can say R naught equal to 2K ZE square divided by your kinetic energy. You can write this way also, that 2K ZE square divided by Ke half of mv square. Numerical they are generally not asking. Here they have asked till now theoretical question, like they can say distance of closest approach, R not proportional to, we can say 1 by kinetic energy, R not proportional to 1 by m, R not proportional to 1 by v square, R not proportional to your okay, Z1 into Z2. Okay, because this is having, suppose we can say Z1, this is having the Z2, you use other particle, then Z1 into Z2. Some theoretical, okay, like this. So if you remember just this line here, okay, you will be able to solve your question. And this is not the things to mug up. Just you remember that Ke equal to P, kinetic energy equal to the potential energy. So this information is enough in the your Rutherford model. Theoretical things already you know from the chemistry. Now we'll go for the Bohr model. Okay, in the Bohr model you have to remember first of all, okay, that only for the single electron system, okay, only for the single electron system, not valid for the multi-electron system. Okay, now sometimes they can say in the statement assertion region that okay, Bohr model is there and one is the your planet model. Okay, so planet model and Bohr model, what are the, okay, why we cannot apply exactly same thing in the your okay, Bohr model? Listen, in case of planet model, if you take na, then this is the sun. Okay, only for the theoretical question, if they want to make very good question out of this. And then here we have these planets, okay, like some one planet here, other planet will be in this orbit, suppose here. Okay, now you know that interaction of the sun, here we are writing this force, and this force we write here G m1 m2 divided by your r square equal to, we can write simply mv square by r. So here this planet to planet interaction is very less. Okay, planet-planet interaction is very less as compared to the sun-planet interaction. Okay, planet-planet interaction. Okay, this is the line of NCERT I'm saying. Okay, planet-planet interaction is okay, very less as compared to sun planet interaction. Okay, sun planet interaction. Okay, so if this interaction is very less, very less, negligible. Okay, so what we can do, basically we can ignore this, we only consider this interaction here, we don't take that interaction. Okay, yes, but in case of Bohr model, if I say, then here what happens, that this is the your nuclei, and here we have this electron and we have this electron. Here this interaction will be, okay, if you take this interaction, this will be the kZe square by r square. This interaction, if you take electron interaction, this will be the Ke square by r square. Can you see here electron repulsion is very less, because you know this is just Z times, this is the Ke square by r square, and this is how much here, kZe square by r square, means this is Z times. Z can be 10, 20, 30, 40, 50, 100 like this. So this is just 40, 50, 100 times, and this interaction cannot be ignored here. This is the one difference. Okay, here planet interaction very less can be ignored, but here this cannot be ignored. Okay, so one difference is there in this planet model and your atomic model. Okay, then we can say radius in this one. Okay, given by this 0 point. First of all, let me say that here we are writing for the single electron system. Okay, because electron interactions are significant, we cannot ignore. So if you keep some more electrons, then electron interactions you have to consider, but you cannot take those calculations. That's why we take the single electron, and then we write this one, that mv square by r how to be equal to your kZe square by r square. This is the equation number 1. Second equation, you know, angular momentum how to quantized, which is the nh by 2 pi. Always remember that angular momentum mvr equal to nh by 2 pi. In any of the stable orbit, these two equations how to be valid. These equation must be valid. If these equation not valid, then this cannot be your stable orbit. So for stable orbit, okay, for the stable orbit, equation number 1 and 2 must be valid. And if these two equations are valid, then energy of the electron will be constant in that orbit, it will not radiate the energy. Okay, our whole discussion will be based on these only. Okay, so stable orbits in which equation number 1 and 2 valid, and electron is not going to radiate any energy of the electron is going to be constant in that orbit. Okay, now we can write here, for using these two we are going to get some formula here. Okay, so I will say in this one, like okay, if you, okay, very simple one, you can get the things here. R equal to, I can write this becomes 0.529 n square by z angstrom. Okay, means here this is the radius. By putting the data, this will be 2.18 into 10 power 6 z by n meter per second. These two only you have to keep in the mind, rest you can always calculate. Okay, suppose they are asking about the radius, we can find. They are asking about the velocity, we can find. Like if I take the question here in this one, okay, question I'm taking here, find radius and velocity in third orbit of Li plus 2, because they will always give this thing that a single electron should be there. So we can say this Z becomes basically what? Z is your 3 and N is your 3. So we can say radius becomes 0.529. N square means 9 divided by 3. Okay, you can do the calculation here. So we can say it is the 0.53 into 3. This way you can write. So this becomes 339, and then we can write it is the 15 0 point, okay, 1.59 angstrom. Velocity if they are asking, then we can write 2.18 into 10 power 6. Z, which is the 3 and this is the 3, so we can say it becomes simply 2.18 into 10 power 6. After this, whatever they are asking, suppose they are asking angular velocity, you can say angular velocity is simply omega equal to, okay, you know, V equal to R omega. V equal to, you remember this formula always, V equal to R omega, because omega will be equal to how much here? V by R, okay. V by R, you can put the data. Can we get this thing omega? Yes, we know the V, we got the R, we can say V value 2.18 into 10 power 6 divided by R, we got here how much? 1.59 angstroms, we can write 10 power minus 10. You can solve this one, okay. If they're asking angular frequency, we can say omega equal to 2, means angular frequency omega. If simple frequency, then 2 pi f. Time period, then we can say omega equal to 2 pi by t. We can easily get the any of the calculation if they are asking, we can find. Now, sometimes they will ask ratio based question. So you can say, sir, radius is proportional to n square by z, velocity is proportional to z by n. So if I say omega, then omega will be proportional to v by r, and from here we can say v is z by n and r is n square by z. So you can say omega is proportional to z square by n cube. They can ask about the time period. We can say time period omega is, here we can write in this one simply 2 pi by t. So we can say time period becomes proportional to n cube by z square. But if you have to calculate time period anywhere, if you have to calculate the time period, okay, this is a ratio we can find, okay. But time period always you will write anywhere 2 pi r by v, okay, time period total, okay, this orbital. It is moving in this orbit, so we can say it will be traveling how much distance? 2 pi r. With what speed? V. So 2 pi r by v you have to use if they are asking the numeric data. Otherwise, we can say this one is proportional to this thing here. They can ask what is the current, then we can say current will be your I, it will be equal to charge by time and cube, okay. They can say your magnetic moment, okay, so we can say it will be simply equal to your I into A, okay, I into A, so we can say this magnetic moment M proportional to I is Z square by N cube. A is the area means pi R square, okay. Okay, this is the I into pi r square. R square, if you put na there, R square from there, we can say it will become n power 4 divided by, okay, z square. In this one, you can say n square by z. So from here, we can say magnetic moment is directly proportional to n. So you will remember magnetic moment and angular moment. Magnetic moment and angular momentum both are proportional to the principal quantum number. Both are proportional to L proportional to N, M proportional to N. Okay, your L means here angular momentum. If you see the previous one here, okay, we have written angular momentum is proportional to N. Okay, this one we can write L equal to NH by 2 pi. So L is proportional to N, and your okay, magnetic moment also proportional to N. These two things are proportional to N. Keep in this thing in the mind. Okay, angular momentum, magnetic moment, both proportional to N here. Okay, clear? If they're asking the formula, you can say I you can put here E by T. If they're asking the numeric value, okay, then we can find from here I A. Okay, so one is the in the Bohr model. This type of questions. Another type of questions are actually based on the spectrum, that whenever any electron makes transition from higher level to the lower level, any of these lower level, okay, then it will be emitting some radiation, okay, possible radiation from any level. We can say 1 by lambda equal to R, it will be equal to 1 by n1 square minus 1 by n2 square, okay. If you are writing for any hydrogen like, then we can write here R z square. So 1 by lambda equal to R z square, 1 by n1 square minus 1 by n2 square, okay. I will take directly one question on this one here. You need to remember first thing that, okay, there is the one thing which is the first line, okay, and one is the last line, okay. What are the first line? That if transition from the nearest, okay, if transition from nearest. Okay, when transition happening from the nearest line, that is the known as first line. Okay, last line we can say transition from the, okay, when transition from last. Okay, when transition from farthest, or we can say last. Okay, when transition from the farthest or last, that will be basically known as what? Last line. Clear? Now, let me take this one here. They're asking question, find ratio of last line of Lyman to first line of Bastian. Okay, everyone knows Lyman, Balmer, Bastian, bracket, fund. Okay, this thing you know. So we can say that this one is the here. Okay, Lyman, you can say this is the Balmer, then this is the, okay, Bastian, bracket, fund. Okay, means this one we can say it is the coming to this level, Lyman coming to this level, we can say Balmer coming to this level, this is the Bastian. Okay, like this. Now we can say first line, last line of Lyman. Last line means coming from the farthest. Coming from the farthest means coming from the infinity. When it is coming the farthest, what is the farthest thing? You can say infinity. When coming from the infinity, then we can say this will be the last line. Remember this thing? And in the last line, energy is going to be the maximum. Okay. In the last line, energy going to be the maximum. In the first line, energy is the minimum. They can use this thing also. So we can say here, remember, in the last line, energy maximum. Okay, and if energy maximum, wavelength will be minimum. So they can say maximum wavelength, wavelength of maximum energy. In the first line, we can say energy will be the minimum. Okay, because gap will be less, and we can say wavelength is going to be maximum here. Okay, so remember these lines. They can use the first line, they can use the last line, they can use okay, maximum energy. Last line means gap is huge, and if your gap is huge, it means energy is going to be what? Max. Energy will be the max, wavelength will be the min. And if they are saying the first line means very close, and in the very close, then we can say your okay, energy difference will be less, and wavelength is going to be max. Okay, so let's go back to the question here. Last line of okay, Lyman's, we can say it is coming from infinity to 1. Okay, so we can calculate here first of all for the last line of Lyman. It means transition is basically from infinity to 1. So we'll write here 1 by lambda 1 equal to r. Okay, we are solving for the hydrogen, z equal to 1. Okay, so 1 by 1 minus 1 by infinity. So you can say this becomes here lambda 1 equal to, simply in this one, how much? 1 by r. Okay, now then we can say first line of Bastian. Okay, first line of Bastian. Okay, first line of Bastian means this is the Bastian, and for the, this is the Bastian. Okay, this level. Okay, this level. Now we can say for this level, nearest is this. It means transition is okay, this is the 1 2 3 4. Transition will be from the nearest. Nearest means your 4 to 3. So here we can say transition is actually from 4 to 3, and now we have to calculate. So we can say 1 by lambda 2 will be equal to r, and here we can write 1 by 9 minus 1 by 16. Okay, you can say 1 by lambda 2 equal to r. This will be the 144. And here we can write 16 minus 9, which will be the 7. So lambda 2, you can write 144 by 7r. Okay. Now we can write from here that ratio we have to find. So we can write lambda 1 by lambda 2. Okay. Lambda 1 by lambda 2. Can you get the relation here? Yes. Lambda 1 by lambda 2 becomes in this one how much? Here we can write 1 by r, and here we can write 144 by 7r. R you can cancel. This becomes 7 by 144. Okay, and what language they can use here? You know, they can say the maximum energy wavelength to the minimum energy wavelength, or maximum wavelength to the minimum wavelength. Okay, maximum wavelength to the minimum wavelength. Clear? This type of questions can be done. Possible? When you do na? Okay, let me write one more question here similar to this. I will not solve. Okay, just I'm writing here. Okay, they are saying suppose find ratio of of max wavelength of Balmer to min wavelength of bracket. Okay, you can say same thing that here in this pen. Okay, you can always draw this way. Okay, you can write this is the your okay Lyman Paschen okay means Lyman Balmer, then we can write here Paschen, then we can write this one in the your bracket, and then we can write this is the fund. Okay, in this question they are asking about the your okay which one? Balmer. Okay, so we can say for the Balmer they are saying here, if you say maximum wavelength. Maximum wavelength means minimum energy. Minimum energy means transition from here. Okay, so we can say for the Balmer, if you take maximum energy means maximum wavelength means minimum energy. Okay, lambda max energy min. Energy min means nearest one, and nearest one will be what? Here this is the 1, this is the 2, this is the 3, so 3 to 2. 3 to 2, you can, I hope, calculate 1 by lambda equal to simply here r 1 by 4 minus 1 by 9 calculation you have to do. And if I say for the bracket they are saying what? Minimum wavelength. You know lambda is minimum. If lambda minimum means energy is going to be what? Maximum. And energy maximum means transition how to be from. If energy is maximum, then in maximum you will get when transition from the infinite. So we can say here it has to be transition from here, and in that case, okay, we can say for the bracket it is coming to this level. So we can say infinity to 1, 2, 3, 4. Here you can write infinity to 4. Okay, and 1 by lambda 2 or 1 by 16 minus 1 by infinity. I hope you can calculate over. Okay. Now I will add here. I will go to the next. Here you have to remember your formula for the potential energy. We can say this is the okay your minus kZe square by r. If I say your okay total energy, then we can say this becomes kZe square by 2r with the negative sign, and kinetic energy becomes half mv square. Okay, and we can write this one becomes kZe square by 2r. Okay, these relation you have to remember. Similar formula in the gravitation also you have seen. Okay, ratio you need to remember potential to the kinetic to the total they can ask. So we can see here, and this one is the minus 1, this is the 1 by 2, this one will be minus 1 by 2 if you make it simplified, minus 2, this is the 1, and this is the minus 1. Here graph you have to remember same as the gravitation. We can say this will be the graph of Ke, this becomes graph of P, and this is the graph of total energy. Okay, so these graphs you have to remember. Here I will add one more line because here they are asking, a lot of people do this mistake that this is the your R. Okay, so they can say H R increases, or they can say as N increases. So as R increases or N increases, you know, if you are going this side, then your K is going down, kinetic energy decreases. Okay, so we can say K decreases, means velocity also decreases. Okay, but your potential energy graph, if you say potential energy graph is going up, total energy graph is going up, so we can say potential energy increases as well as total energy increases. So this thing you have to remember, as we go to the higher orbits, as you are moving to the higher orbits, okay, or your orbital radius increases, you move to the higher orbits, your K decreases, velocity decreases, but your potential and total increases. Okay, potential and total will increase. Clear this thing? Okay. Now, you have to know energy, okay, for if I say in this level here, okay, then you know your energy is going to be in this one. Total energy, if I write minus 13.6 electron volt. If I write here K, then you can say with the plus 13.6. And if I say potential energy, then it becomes minus 27.2 electron volt. This one I am talking about N equal to 1. If you talk about your N equal to 2, then we can say in the N equal to 2, Total energy in this case becomes minus 3.4 electron volt. Kinetic energy will be plus 3.4 electron volt, and potential will be equal to minus 6.8 electron volt. Okay. Then we can say for n equal to 3 here. Okay. Your total energy here in this one. Okay. These values should be remembered whatever I'm writing. Okay, total, kinetic, and potential. You can just remember using that your ratio also. Total, everyone knows 13.6, 3.4. I hope you know this thing. Right? Yes, 13.6, 3.4. Then here we create 1 point. Okay, 1.51. Okay, then we create this K becomes 1.51, and then potential becomes minus 3.02 electron volt. Okay, like this you can write for this level also. Okay, here we can write, and then okay, so on. They will ask here in this one questions. One thing you remember, the difference also. Here to here difference should be remembered all the time. This is the 10.2 electron volt. Here difference is 12.09 electron volt. We can write roughly as 12.1 electron volt. And this difference, okay, between 1 and 4, 12.75 electron volt. Okay. This one you have to keep in the mind. Okay, here 10.2, 12.1 and 12.75. Okay, these difference must be there. They will say assume potential energy to be zero in ground state. Okay, assume potential energy to be zero in the ground state. Okay, then they can ask energy, okay, in any of the state. Then okay, then find okay, find total energy, then find okay, find total energy in first excited state. Okay, first excited state. Now they are saying assume potential energy to be zero in the ground state. Generally we take potential energy, okay, zero in the infinity. Here potential energy we are taking how much? Minus 27.2. They are saying make this, assume this energy to be zero, then you have to calculate. If you are changing the potential energy, we are not changing the kinetic energy. Kinetic does not depend on the reference. Potential we can change. You know, when you change the potential, total energy automatically changed. Total is equal to what? Kinetic plus. Total is always equal to kinetic plus potential. So we can say potential you are modifying, total modified. So you will modify potential as well as total to make it zero. To make this thing zero, how much you will add? 27.2. So this becomes zero. So now you are going to add 27.2 everywhere except kinetic. Okay, in all the levels will be modified by the 27.2 except kinetic. All the levels will be modified except kinetic. And how much you have to add? 27.2, because they are saying in the ground state you have to make it zero. So they are saying that in the first excited state you have to make it zero, then we can add 6.8 everywhere. Okay, so I will be adding here also 27.2. okay, in this one that becomes your plus 13.6 electron volt. Here we can add a 27.2, here we can add 27.2, like this we can add. So we can say here energy 27.2 minus 3.4. okay, this will be the energy in the your first excited state. They can ask in the first excited state or ground state or any of the state. Can we do this thing? Possible? Now number of lines, already you know that number of lines, okay, from any level is n minus 1 by 2, okay, or we can write in terms of delta n plus 1 by 2, we can, but remember this difference should be very clear to you, okay, that they will say that electron absorbs 12.75 energy. I will take one question here, okay, that here 10.2 minimum is the this, okay, from the ground state I'm saying minimum, okay, in the ground state they can say minimum absorption, then we can see the ground state minimum absorption is how much? 10.2. Then how much? 12.1. Then how much? 12.75. If goes to infinity, then 13.6. So in the ground state, this is the minimum absorption, 10.2. In the ground state, less than 10.2, absorption will not happen here. Minimum is the 10.2. Now I am saying here that okay, electron absorbs 12.75, okay, okay, in a ground state. Once it is written like this, that 12.75 in the ground state, then you can clearly say that okay, particle actually reaches 1 to 4th level, okay, 1 to 4th. Then they can ask, then okay, then possible transition, okay, possible transition they can say, okay. Then we can say it once it goes to this level, na, here, okay, here to here. Now from here it can come down here, it can come down then here and then here, or it can come down okay, first of all here, then it can come down here directly here like this, or we can say that it can come down here, okay, like these, okay. So many possible combination you can say, or it can come down directly also, this way you can make. If they are asking how many transition possible in this one, then you can say here delta n becomes your 3, and we can write number of lines. If they are writing, then 3 into 4 by 2, that becomes total, it will be the 6 lines, okay. So this is the one simple question, that 6 lines possible. They will ask what is the minimum energy of this transition. Minimum energy of the transition, you can say like this is the 1 2 3 4. Here energy minus 13.6 minus 3.4. Here we can say 1.5, I'm writing, okay, and here we can write minus 0.85. So you can say this will be the minimum energy, 0.85 to this 1.51. This difference you have to take, that is the minimum energy. Minimum energy is here in this one, okay. This is the your minimum energy here, okay, and this difference between the 0.85 and 1.51 will be the minimum energy. So they can ask how many transitions are there, okay, and what are the minimum or maximum over here possible. Okay, one more thing you will remember here in this one, that absorption, okay, absorption happens in the ground state, okay. So absorption, okay, will be in the ground state, okay. And if absorption happens in the ground state, then okay, in absorption spectrum, only we are going to get Lyman, only Lyman we are getting, okay. Some evidence, some practical suggests that we get little bit Balmer also, but for our syllabus we will only take the Lyman, okay. If question asked, then you have to take the Lyman, okay. Then in the absorption we are going to get the Lyman. But in emission spectrum, emission possible for all, so we are getting all lines, okay. So you will remember that in the emission spectrum we are going to get the all lines, but in the absorption we are going to get what? Lyman. Lyman is corresponds to UV, okay. Lyman corresponds to UV, okay, for the hydrogen spectrum. For the, okay, we are talking about the hydrogen here, okay. So here your atom is also over, all the important things whatever is there we have done. Now it's done for the nuclei, okay. In the nuclei we have only two things, one is the binding energy and one are the your okay, reaction part here. So if I say first of all here in this one about the nuclear size, you will remember that radius is given by r naught, okay, a power 1 by 3, okay. Here r naught is always equal to 1.2 fm, means it becomes 1.2 Fermi meter, means 10 power minus 15 meter. Using this we can estimate radius of any of the nuclei. They can ask here ratio based questions in this one, like okay, so you can clear, okay, question they are saying that one nuclei is the x here, okay, we have this one 5 and other nuclei is the y, and this is the 39, okay. You can easily tell which one we are taking, and they are saying find ratio of, okay, ratio of nuclear radius, okay, ratio of nuclear radius. Now we can say R1 by R2 is going to be equal to your A1 by A2 power 1 by 3. Now we can say this is the 5, this is the 39, okay, power 1 by 3. 5 power 1 by 3, we don't know. 39 power 1 by 3, we don't know. But you know, 539 will be almost 8 times. 539 is almost 8 times. So we can say here, we can write this one as 1 by 8 power 1 by 3, and now we can say that R1 by R2 from here becomes 1 by 2. So slight approximation you have to consider, you will get the answer. And remember that okay, we assume density to be constant for the nuclei. Okay, everyone will remember density we take to be constant. Any problem? AC is very chill. Let me reduce this temperature. Means increase the temperature. Now we can write here next thing in this one. Density to be constant. Its order you will remember. Order is 10 power 17. Okay. Order of density will be 10 power 17 kg per meter cube. Okay. So density for every nuclei is same for all. Okay. Whatever nuclei you take for all the nuclei, it is going to be same for all. Density will be constant, R equal to R naught a power 1 by 3. And okay, we can estimate the here radius. Okay. Now, after this one, you have the questions here that if any of the nuclei is there, okay, and okay, all these nuclei are okay made from these small nucleons. They will combine to form the nuclei. Now to form okay this stable structure, they will release the energy. So here we can say energy released in this process. Again they absorb the energy, then we can say energy absorbed, then they will be okay broken into small pieces here. Okay, this energy, released energy, absorbed energy involved in the process is known as binding energy. Okay, so we can say for the binding energy always you have to calculate the mass defect. Once you have calculated the mass defect, then we can say this energy released. Okay, simply we can write here in this one that okay, q value we can say this is the delta m into c square. But okay, this q value we can write here. Okay, because I'm writing with respect to reactions also. I will not write separate formula for the reactions. So delta m, it how to be in the kg. But if they are saying that this delta m is in the AMU, then we can use delta m into here 931.5 MeV, and here delta m is in AMU. Okay, so these are the two formula you have to use, whether they are asking for the binding energy, either Q value or anything. This question will be, means this thing will be applicable everywhere. Okay, like let me take the question here. And if anywhere, okay, now let me take the your nuclear reactor, okay, because they're also same formula used. If they're asking the power, then power simply we can write energy by time. Okay, if they are asking the power of any of the reactor, then we can say simple power will be equal to energy by time. We will use the same formula. Mass defect can be in the kg, can be in the gram. Okay, they are saying in a nuclear reaction, 1 kg uranium converts to 999 gram uranium in 1 hour. Okay, it means we are taking 1 gram uranium, but okay, now we get finally 999 gram. Okay, or 999 gram, okay, product we can write, okay, like this. Because you know when uranium will be okay having, then it can divide into barium or krypton, okay, plus some neutrons, and these barium and krypton are not fixed. These are the probability based, and anything can be possible here. Uranium divides into barium krypton. Other than barium krypton possible, we say we write here 3 neutrons, but always 3 neutrons not there. Okay, sometimes 3, sometimes 2, sometimes 1. Average number of neutron if you take in the reaction will be 2.5. okay, average 2.5. okay, this amount of energy also keep on changing. These product also keep on changing. These are not always barium and krypton. Mostly we are getting, so we are writing in the barium and krypton because something we have to write, but not always barium and krypton product can change. So they are saying in this reaction 1 kg uranium you are using, out of that 999 gram product you get. It means how much is the mass defect actually in this one? You can say that out of the 1 kg 999 gram we have the product, so mass defect is simply equal to 1 gram. Okay, now you got mass defect 1 gram, so we can say energy we can calculate delta m into c square. They're asking find power of the reactor. Okay, find power of reactor. Now we can see here that Q equal to will be equal to in this one 10 power minus 3. This becomes 9 into 10 power 16. Power will be equal to simply energy by time. That becomes 9 into 10 power 13 divided by time 1 hour. So you can say 1 hour is the 60 minute. Okay. So 60 into 60, you can write 3600 seconds. Okay. Possible, easily we can calculate. Okay, this is the question number 1 here. Okay, they have given the your initial and final, so we can take the mass defect always initial minus final. We calculated the energy, and here this energy is in the joule because we have taken the SI unit. That's why this power will be in the watt. Okay, I will take next one. Okay, they will say annihilation. Okay, one process means is there that is the annihilation. Annihilation means completely destroyed. Okay, that total. Okay, total will be destroyed. Okay, and if total mass is destroyed, it means mass defect is equal to the total mass. Like I can say your okay, helium particle is there, and helium particle is totally destroyed. Okay, now you know that if helium particle is totally destroyed, then how much mass is there? They can say helium or they can say your alpha particle. You know it is having mass. They will give okay if they want. Otherwise, you can take. I'm writing the question. Find energy released if alpha particle annihilated. Okay, alpha particle annihilated means your okay totally destroyed. Okay, alpha particle is nothing but the nuclei of helium. Okay, helium nuclei destroyed. Its mass you can take if you don't okay they are not giving exactly, you can take 4 AMU. Means 4 AMU total mass defect will be there. Okay, now we can write how much energy is going to be released. We can write this value will be 4 into 931.5 mega electron volt. Okay, if alpha particle destroyed, you know they can ask for the alpha particle, they can ask for the beta particle, they cannot ask for the gamma because gamma is not the particle, gamma is the already energy. Okay, we'll talk about this one. So second question I will take here that find okay energy equivalent to beta particle. Okay, now I can say the same thing that beta particle destroyed, then how much energy is there? Or I can say your energy equivalent to beta particle. This is also known as your rest mass energy. Okay, energy equivalent to beta particle. We can say this is the your rest mass energy. Okay, so they can use these different words: rest mass energy, energy equivalent to beta particle. You can see here this will be equal to in this one your same delta m into c square, and beta particle mass is 0.00055. Okay, this mass first of all should be remembered. If you don't remember, then okay you will, and when you multiply then you get 0.51 MeV. Okay, at least this data you have to remember that okay if electron or beta particle is destroyed or energy equivalent 0.51 MeV. Okay, 0.51 MeV. Clear? Okay. Now, sometimes we'll be having the reactions. They will be saying like this that okay, one is the X220. Okay, it divides into two parts. Okay, X220 because it is a heavy. It how to get the stability? So it will divide into two parts and. Okay, these two parts can be similar or they can be your different parts. So two questions, one I will take the similar, one I will take the different one. So 220 okay divides into similar parts. Okay, so similar parts means 110 plus 110 means okay we are going to take we are going to get 2y. Okay, identical one. Okay, so 220 divides into two identical parts. Okay, it can be identical, it can be the different. They have given here in this pen binding energy per nucleon. Okay, they are saying suppose this one I am taking the EG data 5 MeV per nucleon, and here they have given this is the suppose 6 MeV. Energy release they are asking, always energy release in these processes you will write binding energy final minus binding energy initial. Okay, total binding energy final minus total binding energy initial. So we can write here in this one, this is the binding energy per nucleon given. Okay, so how many nucleons are there? We can say 2 into 110 means 220, and each nucleon is having 6 minus we can write here 220, and each nucleon is 5. So we can say answer will be in this one 220 MeV is the total energy released in this process. Okay, yes, completed all. Okay, important questions we are writing already. Means 38 slides we have written, means each slide we are writing almost one question. So listen carefully. Okay, now we have second case. What can be the second case? Second case, it will be the different. Okay, means both parts are not identical. Okay, so suppose if I take another question now, they are saying that this is the x240 and this divides into two different parts, one in the y, one in the z. This one is the your 130 and this is the 110. Okay, either they will give the reaction, either they can say in the language way that 240 divides into two parts with the mass number 130 and 110. Binding energy per nucleon here, okay, they will give you. So we can say binding energy per nucleon is given. Let me take simple values like this 5, 6 and 7. Okay, they will give okay some calculation like 5.2, 6.3, 7.9. Okay, is 7.4 like this, whatever. So we can say in this one Q value again will write binding energy final minus binding energy initial. You can write binding energy final will be how much? 130, and total there are the how many? 6. So you can say in this one 130 into 6 plus here we can write 110 into 7 and minus we can write here 240 into 5. Okay, calculation part you can do. Right? Okay, so we have seen that okay, this is the example of fission. Fission means this can divide into your two identical one. Okay, or we can say this can divide into your okay, one bigger and one small like this. Okay, any based on the probability, anything is possible. We can finish the question. Same thing can be in the fusion also. Okay, so in the fusion they can say like we have 1H2 plus 1H2. Okay, is giving you 2He4 plus some energy released. Okay, they can see here in this one this binding energy per nucleon is let me take this is the A and this is the B for the helium. Okay, they can give the data. Okay, if data given like 1.1, I can take the data also here 1.1, 1.1, and this is the okay around 7 suppose. Okay. Now, so we can say that again here energy release we can write 7 into 4 minus here this is the 2 into 1.2, so total 4 into 1.1. You can say this is the 28 minus 4.4. Okay, 23.6 is the total energy released. Can we do these questions? Okay. Now we'll go for the next one. You know that in the binding energy curve we have actually like this. Okay, this is the maximum, which is the iron. Iron is having maximum binding energy here, and binding energy first increases. Okay, here increasing and becomes maximum for this one in this range 30 to 170. If you say okay, 30 to 170. This one is almost constant. Okay, binding energy almost constant. Okay, almost constant here, and after this one it will be decreasing. Okay, so this side they are unstable because binding energy decreasing, that's why they have the process of fission. This side binding energy is less, that's why this side they have the process fusion, because everyone want to come to this zone of 30 to 170. 30 to 170 they have to come because this is the most stable zone. Okay, 30 to 170 they have to come most stable zone. Here you will remember that what these peaks represents, like these maxima and minima in the graph. So remember maxima and minima in the graph, this is the max, this is the min, this is the max, this is the min, means these peaks or maxima minima in the graph represents electron like okay peaks, or we can say max min, okay, in a B curve represents, okay, cell-like structure for nucleons, okay, cell-like structure for the nucleons, like electrons have no energy levels, like electron have energy levels similar to that one. We have energy levels in the your proton and neutron also. Proton, neutron are not just filled inside the nuclei. Before the Rutherford and Bohr, okay, Thomson said that electrons are just filled. Now we know electrons are not just filled, they have different energy level. So same for the proton and neutron also, they are not just filled, they have the different energy level. Now after each reaction, either your fission is there, either fusion is there, either alpha decay is there, either beta decay is there, your nuclei takes some energy, and when nuclei takes some energy, nuclei goes to the excited state, it will be coming down, then only your gamma is emitted. So we say generally, usually gamma is followed, okay, after this alpha and beta, because once alpha and beta happens, they will go to the higher excited state, they come down, energy released. So gamma is nothing but your energy release whenever nuclei making the transition from higher excited state to the lower excited state. This means energy levels exist within the nuclei, inside the nuclei. For the proton, neutron, energy level is there, okay, and this confirmation comes from this peak, maxima and minima here, okay. Now we'll talk about the your alpha and beta decay here. Listen, I'm going to write here quickly this one, alpha, beta and gamma, okay. So you can see this alpha is just here, okay, like this is the Z, okay, X, Z, A, and we can say Y. If any of the alpha particle is emitted, then you can say this value will reduce by 4 and this value will just, okay, this is the 2 here, so will reduce by 2, okay. Simple, upper value reduced by 4 and lower value reduced by 2. Whenever you have to solve the question, always you will solve, okay. How you will solve that, okay, upper value will reduce by 4, lower value will reduce by 2. First you will balance upper value all the time. After that you will balance the lower value, okay. Alpha is 2He4. Beta is 2 types, -1 beta 0, either +1 beta 0. And they will tell which one they are going to talk about. Gamma is nothing but the energy whenever this comes from any of the excited level to this energy released, okay. Clear here? Energy spectrum of this is line spectrum. You will remember, I'm not explaining this thing. Line spectrum for gamma also line spectrum, and for the beta it is the continuous spectrum. Okay, for 1 week you have to remember. That's it. Okay. If suppose it comes in the examination, you will remember that for the beta it is the continuous spectrum, alpha and gamma it is the line spectrum. Okay, means what are the meaning of continuous spectrum? Energy of beta is not fixed. Beta can have variable energy, while alpha and gamma are having the fixed energy for that particular reaction. Okay, but for the same particular reaction, energy of beta can be changing. Okay, this is because of neutrino and anti-neutrino can take any value of energy. In short, I say, okay, any value of energy, because in the beta emission we get the neutrino as well as anti-neutrino. Okay, but this much is enough here. I will take question in this one. They are saying that this is the your X90 and we got here suppose 240. They are saying this gives you Y, and okay, it is written here that this is the your okay 84, and we can write in this one this is the 208. Okay, 84 and 208, and they are saying that X number of alpha going, Y number of beta. They cannot ask number of gamma. Gamma is simple energy. So X alpha and Y beta are emitted, then we get this nuclei. Now you have to tell me that how many alpha and beta. If they are not saying about the beta particle, which beta particle, you will take the -1 beta 0. Otherwise they will tell, okay, if nothing given, then you will take -1 beta 0 here. So we can write X alpha, it will be the 2He4, and Y, this will be the -1 beta 0. First of all, you have to balance the upper value, then we'll balance the lower value. So we can write here 240 will be equal to, in this one, 208 plus we can write here 4x plus 0. First of all upper value, then only lower value. So we can write here 4x will be equal to 32. From here we can write x will be equal to 8. We got the number of alpha. First upper value you have to balance. Then we can balance the lower value. 90 equal to 84 plus 2x, and here we can write minus y. So we can write now in this one 90 equal to 84, x is 8 here, so we can say 8 into 16 minus y. You can say this 16 and 18, that is the 100, so y equal to, we can write here 10. So 10 beta and 8 alpha. 8 alpha, 10 beta are released. Can you solve these type of questions? Alpha and number of alpha and beta. Okay. Yes. Other things, okay, in the your nuclear reactor, if I say, then you have to remember that okay, best fuel is the plutonium. We are using the uranium, but best will be the your plutonium. Moderators are your heavy water and graphite. Moderator are just going to absorb energy of the neutrons. Highly energetic neutron cannot take part in the reaction. We need to reduce that energy. We have to, okay, make them with the moderate energy. And boron and cadmium rods are used as the controller. They will absorb number of neutrons. Controller will absorb neutrons and moderator will absorb energy of neutrons. This is the difference. Energy of neutron absorbed by the energy of the neutron, okay, absorbed by the moderator, and neutrons are absorbed by the controller. Okay, this thing you will keep in the mind. Okay. Yes, clear. One process last will be the nuclear fusion. And for the nuclear fusion, you will remember that nuclei combine. But for the combination, what should be the reaction? High temperature and high pressure. Okay. High temperature is needed to overcome the electrostatic repulsion, because nuclei, this nuclei positive charge, this also positive charge. There is the huge, okay, there is a very strong repulsion between them. So to overcome this repulsion, they need to have very high kinetic energy that they will get from the temperature, and we need more temperature also, more pressure also, because pressure will be increasing chances of interaction, chances of collision. So high temperature and high pressure required for the process. You will remember high temperature as well as high pressure required for the process. Now we are going for the semiconductor here. In the semiconductor, first of all, you remember that we get okay, these are the your okay, in the solid, if I say, we just now talk, okay, we were talking about the atom. We have the different energy levels in the atoms, different energy level, but in the solid so many atoms are there. Like in the classroom, one student setting, energy will be one different energy will be there. So many students setting, so energy of these students which are setting will be the different. If sitting, then okay, all the students will be having the different. So if I take the set of energy level, then we get it set of energy level of bounded electron, valence electron, is known as your valence band. Okay, so band is nothing but the set of energy level. Suppose in this classroom 20 people are moving, these people are walking, then some will be walking more, some will be okay having this okay fast walk, some will be having slow walk. So we can say these moving particle also will be having the different energy. Moving, we can say these are the free electrons. So free electrons, all free electrons don't have same energy. So set of energy level of the free electron we can define as the your conduction band. Okay, so because conduction band, free electrons are responsible for the your for the conductivity. That's why we are saying this one is the conduction band. So in this one, your valence electrons are there. Here we say valence electrons, bounded electrons, and in this one, your free electrons. And all the free electrons don't have the same energy. This is known as your band gap. This is the delta Eg. Okay, delta Eg is nothing but the minimum energy required to make electron free. This much energy needed, they will become free. You can give more than this, but minimum energy required to make them free. Delta Eg for the silicon 1.1 electron volt, and delta Eg for the germanium is 0.7 electron volt. This data you will keep in the mind. Okay, then we have here your p type and n type. Okay, And we have one is the your intrinsic. You can say, sir, what is the intrinsic? Pure form of silicon, pure silicon or germanium. Pure silicon or germanium is known as your intrinsic semiconductor. In the intrinsic semiconductor, number of electrons, okay, I will draw in the next page. One is the your intrinsic, then we got here p type, then we got here your n type. Okay, now you will remember here in this one your okay, in the intrinsic, if I say it is the pure silicon and germanium, in this one number of electron equal to number of holes. Okay, this number is coming due to, okay, due to thermal agitation, due to thermal agitation means due to temperature, simple, due to temperature. Okay, this is coming due to the temperature, n equal to ns, it is coming because of the temperature. Okay, and here we can say like this. Okay, these are the your holes. If there are the 4 holes, there will be the 4 electrons. Okay, and here average energy level or Fermi energy level will be exactly in the middle. Okay, so this much characteristic you have to remember about the intrinsic. Okay, number same, this okay, energy level will be in the middle. In the p type we are getting basically, or in the intrinsic we are going to do with the trivalent. Okay, what are the example of trivalent? You can say third group. Okay, like this. Okay, this trivalent. Okay, and we can say in the n type we are going to get intrinsic plus pentavalent, and here pentavalent is, okay, these are the example of pentavalent here. Okay, so sometimes they ask the question that what we should add to get the trivalent, what we should add to get the pentavalent, we can get this thing. Okay, now in this one you will know that okay, trivalent will take the okay, if any free electron there, they will take the free electrons, and once they take the free electrons, then they will create the holes. So we can say in this one, okay, what happens that here your number of holes are more, so many extra holes are there. Okay, these extra holes coming because of the doping. Okay, extra hole coming. Okay, trivalent will give the extra hole. Okay, extra holes, we can say holes becomes the majority. Okay, and electrons becomes the minority. Okay, minority due to temperature. Here also some 4 holes and 4 electrons will be there. Okay, now in this one we can say, okay, like this. So you can say minority is there because of temperature. Majority, why whole become majority? Because of the doping. We are doping, because of that only whole become the majority. Earlier both were in the same number. When you will do the mixing, then because of the mixing, here we can say number of hole increase, this becomes the majority. Okay, here we can say energy level. Okay, how to be close to this, okay, valence band. Okay, this one we can refer as the energy level of acceptor atoms. Remember, energy level of acceptor atom, because acceptor atom how to take electrons from here. If this gap is very less, then these electrons can easily migrate from this level. So energy level is very close to the VB, valence band. And here we can write in this one that this is the pentavalent, and pentavalent is going to give the extra electrons. Okay, so this will be giving the extra electrons because it is having 5 extra electrons. So here we can write, due to the temperature some holes are there, some electrons, but extra number of free electrons coming due to this pentavalent. So here so many electrons are there, so we can say here electrons becomes the major. Okay, and holes will be the minor in this one. Energy level of donor will be close to this one because it have to donate the electrons. So if energy, this difference is very less, electron can easily become free. Okay, so energy level is very close to the donor here. Okay, and in this one, number of electrons are more. All semiconductor, all are neutral. Okay, your intrinsic, p type, n type, all neutral. Okay, p does not mean positive, n does not mean negative, all are neutral. Okay, now if they ask here that which will be better out of this one, p type is there, n type is there, here electrons are the majority. Electrons have more mobility. So if they have more mobility, then we can get somewhat better conductivity. So n type is always better than this p type. Okay, so because you can get more current in this one, I'm asking one question here, that if I connect here, this is the p type and this is the n type. If I connect and I am asking that here in this one, that which can have more current, then we can say which can have more current. Here current is IN, this current is IP. We can write IN will be more than IP. Region will be electrons have more mobility. Okay, electrons have more mobility. Here some question comes based on this formula, Ne into NH equal to Ni square. I am taking this question from the NCERT, solved example of that one. They are saying a silicon sample contains 5 into 10 power 23 silicons, okay, per meter cube or per cc, okay, per cc, okay, 5 into 10 power 23 silicon per cc, okay. If it is doped, if it is, okay, it is doped with AS at ppm level, then find number of electron and holes. Okay, if it is doped at the ppm level, then you have to find in this case number of electron and holes in this one. Okay, they are given in this one Ni equal to 5 into 10 power 15. Okay, this is given your Ni. Okay, now 15 or okay, let's take this thing here. So we can write here first of all what are the meaning of ppm level. Okay, they are giving here your ppm level in this one. So we can say 10 power 6 silicon, we are mixing 1 arsenic. If 1 silicon, then you will mix here 1 by 10 power 6 arsenic. We have here 5 into 10 power 23 silicon. So how many arsenic needed for this one? So you can say 1 by 10 power 6 into 5 into 10 power 23. Okay, so now we can write here in this one, for this how many silicon will be needed? Yes. Clear? So these many silicons will be needed, these many your arsenics are required for the process here. Okay, means we can write here in this one 10 power 6 silicon, then we are getting how many? 1 arsenic. Okay, because ppm means your parts per million. In the 10 power 6 silicon we needed 1 arsenic, so 1 silicon needed 1 by 10 power 6 arsenic. So 5 into 10 power 23 silicon requires how many arsenic? These many arsenics are needed. Okay, and here in this one, arsenic, number of arsenic will be equal to number of electrons. So number of electron will be 5 into 10 power 17. Okay, means these many electrons are there. Okay, 5 into 10 power 17. If they are asking here number of electrons, then we get Ne into NH equal to Ni whole square. So we can say NH will be equal to Ni square divided by your Ne. We can write here 25 into 10 power 30. Okay, divided by, we can write this number 5 into 10 power 17. So you can say this one becomes 5 into 10 power 13. I hope this one is clear. Yes. So one solved example of NCERT, this is important also. And EG also, maybe they will ask just number of electrons. We can say number of electron, if they are asking, it will be equal to the number of arsenic. Arsenic being the pentavalent will give you these many, almost equivalent to these many your electrons. So we can say 10 power 6, 1, so 1 will be 1 by 10 power 6. So 5 into 10 power 23, 1 by 10 power 6, 5 into 10 power 23. Okay, these many arsenic will give you these many your electrons, and then we can use Ne into NH equal to Ni square. Okay, clear here? After this, in this one we have the p-n junction. Okay, in NCERT they are saying that we cannot join p type and n type to get the p-n junction because flow of charge carriers will not be continuous. Okay, regarding the p-n junction, if I say, you will remember few things I will add here, that in this p-n junction, okay, once you, okay, this side you are doping with the p type and n type, okay, then what will happen here, that as soon as you will, okay, dope this one, then majority, okay, because of the diffusion, they are going from higher concentration to lower concentration. We can say this side so many holes are there, along with the hole we have here acceptor, that is a negative, okay, hole, negative, hole, negative, hole, okay, like this. So this side, okay, now holes are there, and this side we have the your donor atom, okay, which is the positive electrons, positive electrons. Now, like this. So what happens as soon as they are moving, okay? So diffusion will be happening due to diffusion, and diffusion happening due to the high concentration, okay, high concentration to low concentration, we can see. So diffusion happening both side, holes are diffusing, okay, holes are diffusing your p2n, and electrons are diffusing n to p. Okay, holes are p side more, so from p side they are going n side, and electrons are going from n side to p side. So diffusion current, you have to remember, it is from p to n. Okay, so diffusion current due to the majority carrier, it is the p to n. Okay, diffusion current will be from p to n. There will be another, okay, drift current, that will be because of the minority. This direction is n to p. Drift current is very less. Diffusion was initially more, and with the time diffusion will keep on decreasing, because what happens that as soon as these electron and hole will recombine, that in this junction here your positive and negative ions are there. Due to this one here, internal field developed, and this internal field will oppose the diffusion process. You will remember this internal field En opposes diffusion. Okay, it opposes diffusion and supports drift. Okay, it will support the drift, but it will oppose the diffusion process. Okay, clear? Now, so what happens that we don't get any net current, means I net actually becomes zero. Okay, so in the p-n junction, okay, net current is zero here. And if I say in the depletion layer, then you have to remember, in the depletion layer, this is a thickness 10 power minus 6 or minus 7. Okay, and in this one, positive and negative immobile ions are there. Okay, immobile ions. Okay, no charge carriers. Okay, no charge carriers, because charge carriers already recombine. Electron holes not there in the depletion layer. What is the meaning of depletion? That electrons and holes depleted means they already combined, so we have only positive and negative ions in the depletion layer. Okay, so what are the depletion layer you got here? Okay, and we got in this one, what current is the diffusion current from p to n, drift current from n to p. We got there is no net current. En will oppose the diffusion and supports the drift here. Okay, here we have some barrier also in this one, some potential barrier exists in this one, and that we can say it will be equal to your dv by dr. Okay, equal to dv by dr. They can ask here like okay, suppose example I am saying V equal to 0.6 volt, and they have given the dr equal to 10 power minus 7. They are asking what is the strength of the field. We can say 0.6 divided by 10 power minus 7, which becomes 6 into 10 power 6. This much strong field is there at the junction. Means strength of this field is going to be very, 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 very strong. Because of this field only, diffusion stops and your diffusion becomes very, 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 very less. That's why net current is not there. To get the current, we are doing the biasing, and we have two types of biasing. One is the forward bias and one is the your reverse bias. Okay, how to identify? In the forward bias, P we are going to make positive and negative, means P will be high. Okay, if P high, then we can say it is the forward, and here we can say just to make it reverse, P negative and positive means your N is going to be high. Okay, if N high, then we can say that the reverse. If this one P high, like they can say here some examples I can take on the next page like this. They are giving like this one. This is the 5 volt. This is the 3 volt. You can say P is high. That's why this will be forward bias. I can take like this. This side it is earthed, and this side we are writing 2 volt. You can say this side 0 volt, this side 2 volt. This one becomes reverse bias. Okay, we can take this example here. In this one, this is the -2 and this is the your -3. You know, that side more and that side more means this becomes your forward bias. Okay, so these 3 examples are enough. If P high, then we can say it is the forward, and if P is low, it is the reverse. Okay, means N is high, it is the reverse, P is high, it is the forward. Okay, now you will remember in this one forward, basically what happens, that here we have like this. Okay, so we are going to make the connection. This is the internal field. We'll connect the battery that will oppose. So this P positive. Okay, this is the P and N negative. So P is the positive, N is connected with the negative. Now you know external will be in this direction. So internal and external both are opposite to each other, but here you will say external and internal both will be in the same direction, because this side is the P, this is the N. I can write here this is the P positive, means P negative and positive. So you can say this will be the positive, this is the negative. Both are supporting each other. Okay. Now you remember here in this one, your barrier, because they are in the opposite direction, barrier decreased. Okay. Barrier reduced. Okay. If barrier reduced, then we can say here your resistance also reduced. Barrier reduced, resistance reduced. So current will increase, current increases, current allowed. Okay, current will increase, and you have to remember in this one that width also decreased. Okay, so current increases, all the things decreases here. Okay, here we can write in this one your barrier will increase. It means your resistance will increase. Okay, here your width will be more, and in this one current will become almost 0, means current decreased. Okay, current becomes almost 0 in the reverse bias. Okay, so this difference you have to remember. They can ask what about the width, what about the current. So forward bias will allow the current, reverse bias will not allow the current. Okay, reverse bias circuit you will cut, forward bias you will consider. Like if I take one question in this one, they have given that this is the now resistance and diode given here. They have given here diode and resistance given. Then they have given here another diode, and like this they have connected the battery. This is given, and now they are saying in this one all are the ideal diode. Okay, all the ideal diode means their forward resistance you will take 0. If they have not given the ideal, then you will consider the given resistance. They are saying that this is the 100 ohm, this is the 100 ohm, this is the 100 ohm, and this is also 100 ohm. You will say this is the positive, here positive, here positive, here positive. This one is forward, this one is forward, but this one becomes what? Reverse. So reverse you will cut from the circuit. Reverse you will cut, and if ideal diode you will replace with the plain wire. If some forward resistance given, then you will consider that resistance. Suppose I say na 50 ohm, then 100 plus 50 becomes 150, but nothing given, I will not add. So I can redraw this diagram that like this, upside 100, then we have this one also 100, and then this is the battery, and then here this is the 100. Now you guess this is the simple question of current electricity. Suppose this battery is the 20 volt here. Now we can write in this one that 100 and 100 becomes how much? 50. So this one is the 50, this is the your battery, and this is the 100. Now we can write okay, in this one total resistance R equivalent becomes 150. Current, if they are asking, then 20 divided by 150. Yes, we can do. Okay. Next one we can say here that you have to remember, okay, graph of characteristic of diode. It is actually like this, okay, that in the forward bias current is very less up to some specific voltage. After a particular voltage, current will be increasing. We can say this voltage as the your knee voltage. So current increases after a particular voltage, okay. So this is the forward characteristic, and then in the reverse we know that the current is already very less, okay, very less, okay, almost very less, almost nil variation is there. But after the one particular voltage, because you keep on increasing the voltage, at some particular voltage lattice breaks, and when lattice breaks, what happens? Sudden increase in the charge carrier, because so many charge carrier will become free, current increases suddenly. That thing is known as your breakdown, okay. So this zone is known as breakdown. This how to be mentioned, okay. They will say in the breakdown current increases rapidly. Under reverse bias, if they are saying in the reverse bias current is zero, but if they are saying in the breakdown zone, under reverse bias in the breakdown, then current increases from the microampere. This current was here in the your microampere to the your milliampere, means becomes your 1000, 10,000 times, anything possible here. Current increases suddenly in this zone. In this zone, we are going to operate our zener, because here potential remain constant. Current can be anything, okay, but potential remain constant, okay. Now you'll remember that these are going to be your non-ohmic devices. You'll remember non-ohmic devices, they don't follow Ohm's law. What is the Ohm's law? V proportional to I, not valid, okay. Ohm's law is V proportional to I, not valid, because you can see graph is not a straight line. V equal to IR I can use, okay. I can use this V equal to IR. We can say your R will be equal to V by I, but here R is not constant. That's why we'll use this dynamic resistance, okay. So we have the, okay, here in this one, our dynamic resistance will be given by delta V by delta I, okay. So V equal to IR we are using, but V proportional to I not valid, okay. This is the non-ohmic devices. They offer dynamic resistance delta V by delta I, okay. We can say here, like if I take one question in this one, suppose it is changing here, this is the point, okay, 8 volt, and this is the 1 volt, then current is changing from 100, okay, this is a milliampere, and here they have given this is the 200, okay. So we can say R dynamic they are asking, so we can say R dynamic in this case, delta V is how much here? 0.2 divided by delta I, 100 to 200 becomes 100 milliampere, and 100 milliampere means how much? 100 into 10 power minus 3, it means how much resistance is there? 2 ohm resistance is there. So they can ask similar question in the forward and in the reverse. Reverse offers huge resistance, okay, because you can see, clear this one. And one more thing I will add here, that resistance is proportional to 1 by slope, okay. Slope of the graph will be di by dv, so resistance is proportional to 1 by slope. Here you can see slope is almost 0, that's why resistance is the almost infinite, okay. Resistance proportional to 1 by slope. And temperature affect over all, okay. Temperature will affect overall characteristic, means temperature will not only affect forward, will not only affect reverse, it is going to affect over all characteristic. This one you will remember. Now going for the zener, okay. About the zener you will remember, it is the your okay, doping high doping. It is in the reverse bias, in the break down, okay, breakdown. It is used for the voltage regulator, okay, because it will give the constant supply, okay, and connected parallel to load, okay, and series resistance, okay, resistance limits current, okay, series resistance limit current, okay. These are the some theoretical point you will remember. Voltage regulator. You can say, sir, what are the series resistance? Listen, this is the gene are always connected in the, okay, suppose this is the your load, and this load you have to, okay, keep secure from any of the voltage fluctuation, okay. This is your some load, some okay, sensitive device you have to protect from the fluctuations. This needs 20 volt, so you are going to connect a zener of 20 volt here. So 20 volt zener you will take, and you will keep in the parallel to this one always, okay, in the reverse bias. If here 20 volt, then across this always you will get the 20 volt, and we can say that this one, okay, RL equal to, if I say your 5 kilo ohm, because the load resistance will be known to you, okay. Here some unwanted fluctuations are there, like we can say, okay, or this one is okay, some fluctuation, or let me take this is the, suppose your 80 volt, okay, they can say 80 volt to 100 volt. I am taking only one data here, 80 volt. You know, here 80 volt, this is the only 20 volt. If you directly connect, this will be burned. So to handle this extra potential, you need to connect here. This is known as series resistance, and this series resistance will determine how much current will be there. If series resistance is very, very high, current will be less. Very less, current will be more, okay. Now we can always find this one, first of all, IL. And how to find the IL? We can say IL will be equal to, in this one, 20 divided by 5, which is the 4 milliampere. Because here you know the potential, you know the resistance, potential known, resistance known. So we can always find this IL. Then we can see here that out of the 80 volt, here 20 volt. So I can get how much PD across this. You can say remaining across this one, that is the 60. It means PD across RS will be equal to 60 volt. So if I say IS will be, so you can say 60 means series resistance. This current is the IS. Series will be equal to, this resistance will be given, like I can say 2 kilo ohm. So 60 divided by 2, that becomes 30 milliampere. Now we can see out of 30, how much going here? Out of 30 here, only 4 going. Means remaining current will go in the zener. So we can write here current in the zener will be 30 minus 4, which becomes here 26 milliampere. You will remember this thing, okay? This type of pattern in the zener. Some theoretical points, okay. It is the reverse bias in the breakdown, parallel to the load. Series will limit the current here, voltage regulator. And if this is the 20 volt will be given here 20 volt, here resistance given 20 by 5, this will be the 4. Out of 80, here 20, so here 60, and then we get 60 by 2 will be here 30. Out of 30, how much current will be going here? 4. Remaining current will go in the zener, okay. This is the your zener here. Now we'll take your 3 devices are there, okay, optoelectronic devices, very simple. One is the LED, next is the your okay, photodiode, and next is the your solar cell, okay. Whatever, okay, I am writing, at least bare minimum you can do, you can remember this much. LED is forward bias, okay. This one is the reverse bias, and this is the your unbiased, okay. What the LED? It converts, okay, your electrical energy to, okay, light. This is used for detection of light. It will detect light, and it converts your okay, solar energy to the, okay, your electrical energy, okay. Now in LED we want that electron hole how to combine. That's why here doping have to be high, doping is needed, okay, in this one LED, okay. And you will remember in this one that okay, what will happen that if you have the high doping, then electron and hole will be moving towards each other and they will recombine. Whenever they will recombine, they will release the energy. Okay, so after the recombination, whatever their energy is there, they are going to release, and this release energy how to be in the visible range. That's why silicon and germanium cannot be used for LED. Okay, silicon, germanium cannot be used for LED. For LED, we are using gallium arsenic phosphide. Okay, this is okay, having gap around 1.9. Its gap, okay, is around 1.9. Okay, and actually you have to choose those materials which have gap from 1.9 to 3 electron volt. These material you have to choose for the LED. Okay, 1.9 to 3 electron volt, roughly this is the range you have to take. Silicon, germanium you cannot take. Here in this one graph is there. It's characteristic of the LED because forward bias. That's why we are going to get forward type graph. And you have to remember, this is the R, this is the G, this is the V. In this IV graph, RGB. Okay, you will remember here. In the photodiode, we can say we are using in the reverse bias. So whenever light will fall, okay, even though light intensity is very less, okay, what will happen? Any light intensity will fall, bonds will be broken, and if bonds broken, when bonds will be broken, when energy of the incident light more than the band gap. Okay, so always remember that here energy how to be, okay, more than equal to band gap, then only it is going to work. Okay, it will detect, okay, more than the band gap. When more than the band gap, then bonds broken, electron hole free, current slightly changes, and if current changes, then we can say yes, radiation coming. So we get a graph like this, that here this is the I1 intensity changed, current changed, again intensity changed, current changed. So we can write at this intensity I1, at this intensity I2, at this intensity I3 is there, and you can clearly say here that this current more, it means intensity will be more. So I3, I2 and I1, and this is the condition that diode can only detect when energy is, okay, greater than this band gap energy, greater than equal to this one. Here what happened that we have to keep, radiation will fall. Okay, so radiation will fall everywhere, but this junction area you have to keep large. Okay, because electric field is only present in this zone. Okay, so here junction how to be large. Okay, large junction we will keep here, because electric field once they are falling, then what will happen? If any electron hole created in this one, this field will automatically separate electron this side, holes this side. It will keep on separating. So this will become the your negative terminal. This will become the positive terminal. If you don't connect any wire, nothing connected. This is the open circuit, and in the open circuit we can say here potential is maximum. So this is known as your maximum potential. We can write this is the open circuit. Okay, voltage. If you connect the wire, then it becomes short circuit, current will flow, maximum current will flow. So we can say if you connect with the plain wire, this is known as your short circuit current here. So we get graph like this for the solar cell, these three graphs, and these okay, bare minimum this much need to be remembered. Okay, because you also know that okay, it in very detail not possible, but at least so that we can put our questions correct in the examination. If you remember this, it will be done. Okay, then last we have here rectifier. Okay, and in the rectifier, you know, one is the half wave, one is the full wave. Okay, so I will say here in this one, your this side half wave, and this side I will write full wave. Okay, in the half wave we have one diode like this. Okay, either this diagram can be given, or somewhere they can give this diagram. Okay, they can give like this. Okay, so either this diagram is given here. Okay, either we can have this diagram. Okay, single diode will be there. Okay, I am seeing because I am not going for the mechanism. Okay, so we can see that whenever single diode, then we can see yes, this is the half wave. Okay, not always. Okay, but if they are asking the question of diode, maybe they will give this diagram. Okay, you can say yes. Now in this one, these two diagram you will remember at least that this one and this one, then this is the your half wave. Here you will remember that if this is the your input, like this, then your output will be, okay, only it is going to convert the your this one will be converting positive cycle, and here output will be the negative cycle. Okay, so these are the two diagram possible. This gives you positive cycle, this gives you negative cycle. So here we are going to get okay, one cycle only like this. Okay, so we can say if input frequency is n, then output frequency is going to be, okay, n. Okay, input is n, then output is going to be n. Okay, like I can say here in this one that this is the your suppose, okay, like this. So you can say when this completes one cycle, this also only completes what? One cycle. That's why input and output also n. While what will happen in the your okay forward, you have your two diodes like this. In the middle we connect our load resistance. That's why name of this becomes your bridge rectifier. Okay, means this one is known as your, okay, center tap rectifier. Another one is the bridge rectifier, which is just like the Wheatstone bridge. Okay, two parallels. You will remember like this, these two parallel, and here these two parallel. Okay, so we can say these two diagram here also you remember, there these two diagram, here two diagram. Okay, this one is known as your bridge rectifier. Okay, now in this one, if your input is like this, then we can say we are going to get both the cycle processed here, negative also, positive, negative. Here you can say when this is completing one cycle, this is completing how many cycle here? Two cycle. So we can see here frequency of input, if input is your n, then output is going to be how much? 2n. If input is n, output is going to be 2n, you will remember. Okay, efficiency, first is this is the most important question actually. They will say 50 hertz because output also 50 hertz. They will say here input 50 hertz. If input 50 hertz, then output will be how much? 100 hertz. This is the important one. Here efficiency 40.6%. Here just double of that one, 81.2%. Okay, clear? And whatever output we are getting in the your half wave and full wave, this is not the perfect DC. So to get perfect DC, or we can say to remove ripples, okay, we use filter circuit. Okay, we use filter circuit like filter coffee. Okay, filter circuit. Okay, means it will filter the ripples. Simple words, it will filter the ripple. And you can say wow, we can make the filter circuit high. You can take the capacitor in the parallel. Okay, capacitor in parallel or inductor in series. Okay, inductor in series. Mostly we use this one, capacitor in the parallel, but if they have given, then inductor in the series. These are the option for the capacitor filter. Okay, clear? Okay, logic gate is the, I think, quite easy one. Everyone is very familiar with that. Okay, I hope possible for everyone. Okay. Now, I will say here your quickly one thing in this one, that whenever you have single input like this, okay, this is the your, okay, NAND. If you make the single input, okay, so this one becomes okay, this one is there, or your this one is there, then always single input, you will remember single input NAND and NOR are equivalent to NOT gate. Okay, single input NAND and NOR are NOT gate. Single input or both inputs same or sorted, they are equal to NOT gate. You will remember. Okay, so for the NOT you have three options. Three option means this is, okay, we can say here what three options you have for the NOT gate. One is this NOT. Okay, we can write here. This is the your okay. We can write in this one. This is the NOT. This is not, this is not, this also not. Okay, this is the not, this is also not, this behavior also not. Single input or both inputs same like this. Here A going, A feeded here also, A going, A feeded here also, means they are behaving like not gate. Okay, I will take questions on this one. Suppose they are writing like this, that we got here, okay, one gate in this one. like this is the one gate we got here, then we got this one, then we got this one, and they are asking what are the output of this one. Then we can write here, this is the AND gate, this is the NOT gate, this is the NOT gate, and this is again NOT gate. Okay, single input NAND and NOR, so not cancelled, and plus NOT becomes your NAND. Okay, so single input things you have to keep in the mind. Single input always like the NAND. Option checking will work in these questions, so you can go with the option checking always. Okay. Now, sometimes they can say the series based question, like they will give you here A, this some signal given here, then we can say this is the B, some signals given here, and then they can ask the different gates in these. Okay, so better we can make the truth table, like if I say this is the here 0, 1, 1 and 0, then this is the suppose 1, 0, 1, 0. So make the truth table, like we can say A value is 0, then this is the 1, then again 1, and then this is the 0. For the B we can make this is the 1, 0, 1, 0. If they're asking suppose OR gate, you can say 0, 1 becomes 1, 1, 0 becomes 1, 1, 1 becomes 1, 0, 0 becomes 0. If they're asking suppose your AND gate, then we can write, we can multiply here, so 0, 1, 0, 1, 0, 0, 1, 1, 1, and then 0. Okay, so what we can do, suppose they're asking the OR, once you made the truth table, we can easily write the OR is basically what? High, 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 then low. But if they are asking about the your AND, then we can say for the AND we'll write what? Low, 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 only then high. This way we can identify. So you have to make the truth table, then you will figure out these things. Yes, possible. Okay, now I will go for the your this part is done here. Polarization. In the polarization, why I am taking this polarization? First of all, reason being because very simple and only two law are there. One is the Malus, one is the Brewster. From these they have to ask the questions. Now, listen. In the polarization, first of all, if I say Brewster's law, okay, what is this law saying? That whenever your light will fall on this surface, and if this reflected ray and your refracted ray, if they are at the 90 degree, they are perpendicular to each other. Normal light we can represent like this using this arrow as well as a dot. Arrow represents parallel and dot represents normal component. Okay, whenever this thing happens, this is not known as your normal light. Okay, unpolarized light. Okay, unpolarized light. Whenever this angle between the reflected and refracted, this is the your reflected here, and this is the refracted. When angle becomes 90 degree, okay, then what happens? This becomes fully polarized and having only dot components. Okay, fully polarized with the dot components. You remember, when this becomes fully polarized, whenever angle between the reflected and refracted is 90 degree, then only it becomes fully polarized. Fully polarized when angle becomes 90 degree. Then we can say this angle is known as your Brewster angle. This is IB. We can say this will be also IB here. Okay, this angle is your R. You can easily say this R will be equal to here in this one 90 minus IB. You will use Snell's law, then we can write 1 into sine IB will be equal to mu into sine R, which becomes cos IB. So you can say 10 IB is equal to mu. So this is the relation of Brewster angle with the refractive index. 10 IB is equal to mu. But condition is important. When this condition happens, when angle between the reflected and refracted is 90 degree, they are normal to each other, perpendicular to each other. Okay. Now here we know that this is always, mu is always greater than 1. That's why IB will be always more than 45. Okay. And max to max it can go up to 90. So more than 45 and will be less than 90. Okay, this is the range of IB. Question they will ask like this one, that suppose if I write here, okay, your mu equal to, they have given okay, root 3, then we can write your what is the IB, then we can say if mu is root 3, then IB becomes how much? 60 degree. Okay, so simple questions will be there. Statement you have to remember that when this condition happens, when reflected and refracted are mutually perpendicular, when they are mutually perpendicular, then this thing happens. Okay, so very straightforward questions. Range they can ask, they can give the value 10 IB equal to me, or directly they ask this is the fully polarized and this one is the partially polarized. Okay, this one is the partially polarized. Okay, this one partially polarized. Okay, now second law is the here Malus law, and in the Malus law we know that if okay, if this is the your here I say this is the okay, we can write here in this one non-PPL light vibration in the all. Okay, and we can suppose this is the your first polaroid here. Okay, so if this is the ordinary light, okay, ordinary light, this is the your I naught, then here intensity becomes your I naught by 2. After passing through a polaroid, ordinary light becomes simply half. Okay, after passing through any polaroid, whatever angle they are saying, if ordinary light is there, non-PPL light is there, intensity directly becomes half after passing through any polaroid. Okay, if they now say that at what, okay, here we are keeping some angle, okay, some polaroid like this, they can say we are keeping at the your this one at the 60 degree. Now how much intensity will be there? They can say 60 degree, 45 degree. Then we can use the formula that now intensity we can write, it will be equal to here I equal to I naught by 2 cos square 60. Okay, I naught by 2 cos square 60. We can say I naught by 2 cos 60 will be 1 by 2, 1 by 4. This one becomes I naught by 8. Here they can change the angle. They can say 60, they can say 45, they can say 30. Known angle will be always given to you. I hope we can do this thing. Yes. Okay, first polaroid, after passing through first polaroid, directly it will become half, and here whatever angle given, we can write I naught by 2 cos square 60, I naught by 2 cos square 45, I naught by 2 cos square whatever angle given. Okay, now I will take next question from the your okay, NCERT. Here you have to remember this data. They are saying one is this polaroid and one is the another polaroid, this is crossed. Okay, these polaroids are crossed. Okay, and here non-PPL light is there. Okay, now what should be angle between these polaroids so that intensity maximum? Okay, what should be angle between, okay, what is angle between polaroid so that I is maximum, intensity maximum? Answer will be 45 degree. You have to keep, okay, you can try using the 30 degree, 60 degree, okay, and okay, whenever this becomes 45 degree, then your radiation is going to be then okay, intensity is going to be max. You have to remember this one. Because in the, if suppose they are asking the same question, then okay, we are not going to check the data. We'll directly put 45 maximum. Okay, means symmetrically placed whenever, okay, in this one. So at the 45 degree, it is the maximum. I will take in this one more question. They are saying one polaroid is, okay, two polaroids are crossed like this, one polaroid, another polaroid is there, okay, and they are saying at what angle, okay, a third polaroid is kept, okay, so that we can get the maximum intensity. Okay, if they are saying that what angle we have to keep, then also we can say you can keep at the your 45 degrees. Symmetrically you have to place, you will get the maximum intensity. Okay, at the 45 degree maximum intensity is there. Okay, now we'll go for the YDSC. In the YDSC, questions of intensity are important this time. I will see here in this one intensity formula. First of all, you have to remember, okay, this is the I1 plus I2 plus 2 root I1 I2 cos phi if identical, okay, if identical source given, then we can write I1 will be equal to I2, and in that case we can write I will be equal to here 2I naught 1 plus cos phi. The same formula becomes 4I naught cos square phi by 2. Same thing we can write like this also, that I max cos square phi by 2, okay. And same thing we can write like this also, 4I naught cos square pi y by beta. These are the formula of intensity. They might ask direct formula of the intensity. You can use for the numerical this formula, either this formula you have seen multiple times, okay, and this one. Here y is distance from central maxima. Distance from central maxima, okay. Now, they will give the questions like this. Okay, I will write in the next page. You can use any formula. You are free to use any one. Okay, they will say if intensity at first maxima is okay, k. Intensity at first maxima is k. Then find intensity at a distance beta by 6. Now, they can say at distance beta by 6. You can use formula, or you can say, sir, this beta by 6 will be equivalent to lambda by 6. And lambda is equivalent to 2 pi. So this becomes 2 pi by 6, means this one is equivalent to angle pi by 3. Okay, equivalent to pi by 3. So we can say beta by 6. Either directly formula is there, you can use that formula. This is the y, this thing is the y, okay, this is the y. You can use direct formula. I am not using direct formula here. So beta by 6 equivalent to lambda by 6. Lambda by 6, lambda is always 2 pi, so 2 pi by 6. And then we can say this one, this is the NCERT exercise question. So we can say pi by 3. Now we can use, okay, you know, maximum intensity is k, okay. First maxima is k, then we can say k is nothing but the 4I naught, okay. K is nothing but the 4I naught. Maximum intensity at first maxima it is the k. And if first maxima is k, means what is the maximum intensity? 4I naught, okay. So 4I naught is equal to k. Then you can use the formula I equal to here 4I naught cos square phi by 2. 4I naught is k here, so cos square phi we can write here in this one, that is the pi by 3 into 2. So we can say k, it becomes cos square pi by 6. Right? Pi by 6 means 30. Cos 30 is root 3 by 2. So it becomes here 3k by 4. Okay. Clear? When you do it, okay, questions like this. So they can say that at the first maximum intensity is k, second maximum intensity is k, central point it is k. We know here intensity is the maximum, and when intensity is maximum, then we can find intensity at any of the point, like beta by 6, lambda by 6. Okay, so beta by 6 will be equivalent to lambda by 6, and then lambda always 2 pi, then 2 pi by 6 and pi by 3. What are the this type of questions are important here? Next type of questions, if I say, that will be related to the fringe width. Beta equal to will be the d lambda by d. So you know that okay, this is proportional to, simple straightforward question. In the medium, if they are asking, then we can say beta will be simply beta by, okay, mu. In the medium, if they are asking, then you will take beta by mu here. Okay, and you will remember that if, okay, this is the source, here we have, this is the S1, this one will be your S2 here, and if you are moving the source, central maxima is here. If you move this source up, central maxima down, if you, okay, central maxima will be always opposite to the source. Central maxima opposite to the source. Okay, central maxima will be opposite to the source. Okay, you remember, if this is upside, this will be opposite means down. When this is the downside, opposite means it will be up. In path of any of the wave, if you keep the slab, in path of one of the wave, if you keep the slab, then central maxima will be shifted in that direction where slab is placed. If you are keeping in the path of up, it will go up. If you are keeping in the down, it will go down. And how many fringes shifted, you will remember that delta x we can say because of this one, okay, mu minus 1 into t. So we can remember like this, mu minus 1 t equal to n lambda. So n becomes here mu minus 1 t by lambda. Number of fringes shifted, this formula will give you number of fringes shifted. So number of fringes shifted always given by n equal to mu minus 1 t by lambda, okay, mu minus 1 t by lambda, okay. So here four things I said, questions related to the fringe width, one this shifting based, and one I said questions on the intensity based, okay. So these are the three important area, okay, here this time. Fringe width always important, intensity I'm feeling this time they can ask, okay. So practice that one. In the diffraction always one type of questions are important, either the formula based, either angular position, okay. So if I say that find angular position of fourth minima, they have given in this one, okay, fourth minima for single slit of width, okay, 2 micrometer given, and lambda is given 5000 angstrom, okay. So this is the 5000 angstrom given. So now we can write here that for the fourth, okay, or let's write it as the your second minima, okay, second minima. Now we can write here in this one that whenever these questions are there, always you write a sine theta equal to, don't use the formula for the angular position, a sine theta, second minima, you know delta x will be equal to 2 lambda. If they are having this one, then you will write here in this one it will be the 2 lambda, okay. Then we can write sine theta will be equal to in this one 2 lambda by a, and we can put the data 2 lambda 5 into 10 power minus 7 divided by a 2 into 10 power minus 6. You know that this is the 10 power minus 6 cancelled, so this is a 1 by 2. So we say theta becomes in this one 30 degree, because 1 by 2 is the 30 degree. So for the angular position, don't use the formula directly, but especially in case of diffraction, angles are quite large. So sine theta equal to theta we cannot write always, okay. So remember this thing, sine theta is not always equal to theta, especially in case of diffraction, okay. So this is the one question important here. Now next one I will say go for the microscope and telescope. In the telescope, if I say first of all, then here you have to remember, okay, if nothing is given, then magnifying power is always equal to, in finite case you will take, and this is the minus FO by FE. And okay, if nothing given, then F minus FO by FE you will take, okay. And length you will take for the normal mode, it is the simply your FO plus FE, okay. I will say only this thing, that because mostly they are going to ask these cases, okay, magnifying power for the infinite case or length. Like if I take the question here, okay, other formula I can say for the D case, okay, FO by FE 1 plus FE by D. Yes, if you remember, good, but bare minimum this one. Question I take here, they have given FO equal to 2 meter and FE equal to 5 centimeter. Then they are asking what are the magnifying power. Then we can write this becomes 200 by 5, okay, 40 times. And then we can write here in this one your length. If they are asking, then we can length will be equal to 200 plus 5, okay. So you can solve easily. And you know, if you want more magnification, for more magnification, okay, you have to remember FO have to be more and FE need to be less. FO more, FE less, okay. FO more, FE less. Like I will take the question here, second question. They can say we got here 100 centimeter, first L1, L2 we got 50 centimeter, L3 we have here, okay, in this manner 10 centimeter, and your L4 is the 2 centimeter. Which one will be best for, okay, which are best for telescope, okay, which are best for telescope. Now we can say for the telescope we need to take FO to be large, as much as large you can take. FO how to be very large and Fe have to be very small. Okay, so we can say in this one, your large value, this one will keep as the Fo, and this one will keep as the Fe. Okay, so these two lenses we are going to consider. One how to be very large and one how to be very small. Okay, done here. Now, next question will take on the angular position. They will say this is the one telescope, because in the microscope telescope mainly questions are in the telescope here. We got this one. They are saying this objective is subtending some angle at this tower, and this tower height is your 10 meter. It is at the distance of 1 kilometer. Okay, so at the distance of 1 kilometer, this tower is there, and it is okay. This is having 100 centimeter, and this is the your 2 centimeter, means focal length given. Fo equal to 100 given, and Fe equal to 2 given. Now they are asking that here, okay, number one, they are asking what is the angular size of, number one, angular size of object. Okay, number two, they can ask for the image, angular size of image. Number three, they can ask here height of image formed by objective. Okay, formed by objective. Okay, now you know this is the objective lens. Objective lens will make, okay, we can write here objective lens will make its image here. Okay, it is making the image here. Okay, this image. So you know that this is the image formed by the objective. This H they are asking. You know, if this is the alpha, this will be also what? Alpha. Okay, so first we need to find the alpha here. So you can write alpha is always going to be the height by distance. This height divided by this distance, and this height is how much here? Your 10 divided by this distance 1000. It becomes 1 by 100 radian. Always remember, when we use theta equal to arc by radius, angle is in the radian. Okay, so we can find first of all alpha. Alpha is the your angle subtended by the object at the objective lens. Okay, so we can write 10 divided by 1000, 1 by 100 radian. They are asking this H now. Okay, you can say here if I use this one, okay, theta equal to arc by radius, because you know this is very far. Okay, it is the 1 meter, this is the 1000. Okay, 1000 times. So we can say this alpha will be equal to here. Okay, this is the first part, clear. Now I'm writing third part, then I will go for the second part. Alpha we can write will be equal to H by Fo. This distance is equal to Fo. For the far object, telescope will form its image at the focal length. Okay, so from here we can write 1 by 100 equal to, we can write H divided by Fo. Okay, Fo in this case is your 100 centimeters, so cancelled. So from H we can write 1 centimeter. Okay, then we can write a second part. You know, magnifying power is always equal to beta by alpha, which is going to be your Fo by Fe. Okay, Fo by Fe. So now we can write here in this one, beta we need to find. Alpha value we can put 1 by 100, so 1 by 100 here. Fo by Fe, you can write here Fo is 100, and Fe I give, I think here 2 centimeter. So we can say this is the 2. So you can write here beta becomes in this case half radian. Okay, so this is the three questions here. How much will be the angular size of the object? What are the angular size of the image? Or what is the, okay, intermediate, this one. Okay, so we can say this is the alpha, this will be also alpha, and this alpha will be equal to H by Fo. Okay, and formula based question, direct formula based question, Fo by Fe and Fo plus Fe. Okay, now in the microscope if I go, then you have to remember in the microscope, okay, magnifying power is simply your MO into ME. This is the formula. In the NCERT they have given this formula L by Fo. Okay, your MO equal to L by Fo, and ME, okay, can be your D by Fe or 1 plus D by Fe, means L by Fo 1 plus D by Fe. Nothing given, then we'll take this formula. Okay, we take always normal mode. If nothing is given, L by Fo, D by Fe, you will remember. Okay, This is for the your image formed at the infinity means normal mode. This one you can say for the stressed mode. Okay, they have given one question: L equal to 100 centimeter, FO equal to 2 centimeter, F equal to 5 centimeter, and D you know by default is the 25. They are asking, so we can say magnifying power. Nothing given. I will calculate for this mode only. You can just put the things 100 divided by FO 2, and here D 25 by 5. You will get the answer here. Okay. So this is the one. Okay. In a text example given in the NCERT like this. Okay, L by FO, D by FE. Okay, if I go for the simple microscope, okay, then we know in the simple microscope you have to remember, okay, here that only one formula, magnifying formula. In case of infinity, this is the D by FE, and if they are asking for the stressed mode, then this is the 1 plus D by FE. Nothing given, you will take only D by FE, and this is a very simple because D is the 25, focal length will be given. Like if I take one example, they are saying that FE equal to suppose okay here 1 centimeter. Okay, let me take 5 centimeter. Then they're asking magnifying power in case of infinity is a 25 by 5, that becomes your 5. Okay, simple formula is that D by FE in the simple microscope. Mainly questions of the telescope are taken 4 variety of question in the telescope, which are the most probable this time. Now I will go for the lens. I'm going in the reverse order, whatever is more important. Now, in the lens, because lens and mirror are quite similar. So if lens is done, mirror will be automatically done. Okay. So in the lens, first of all, you have to remember this formula, lens maker formula, which says 1 by F equal to mu L by mu M minus 1, 1 by R1 minus 1 by R2. Okay. This is known as your lens maker formula. Okay. And mu L by mu M 1 by R1 minus 1 by R2. Okay. Here you will remember that okay, F depends on mu, F depends on the lambda, F depends on the medium. Medium change, focal length will change. Okay. Here we can say your okay, F red color will be more than F violet color because okay, yes, from the mu you can relate. Okay. Now I'm taking one question, and one more thing you remember that if mu of the lens is more than mu of the medium, nature not changed. Okay, nature will not change. Will not change. Nature will not change means convex will remain as the your converging, and concave will remain as the diverging. But if mu L is less than mu M, if medium is dominating, if medium dominating, then nature change. Okay, nature will change means here in this one your converging will behave like diverging, and diverging will behave like converging. I will take one question here. Focal length of convex lens is 80 centimeter in okay, or 20 centimeter in air. Find focal length in water. Now they can just change the medium. Focal length is this much in the air. Find focal length in the water. You will see that 1 by F equal to, in this one, if I write now this formula mu L by mu M minus 1, and this 1 by R1 minus 1 by R2, I am not changing this 1 by R1 R2. This thing becomes what? Constant. I can say is the C. So we can write first for air. Okay. So for the air, if I write, then 1 by F equal to, we can write here mu lens I will take 3 by 2. They will give you that lens made of glass, so that's why 3 by 2. Medium is air, so 1 minus 1 into this thing I am going to take constant C. Okay, 1 by R1 R2 I am not changing, just changing the medium, surrounding medium. Okay, F is 20, so 1 by 20 will be equal to here 1 by 2 into C, so C becomes in this one 1 by 10. Okay, 1 by 10. Now we can write here in this one that if you take for water, okay, so for water we can write here 1 by F will be equal to, glass is 3 by 2, but water index is how much? 4 by 3. So we can write water index here 4, here 3, minus 1 into C. So we can write 1 by F becomes in this one. Your 9 by 8 minus 1, which is the 1 by 8, and C value from there 1 by 10. F becomes 80 centimeter. Okay, 80 centimeter. Clear? Now this question always, that is a favorite question to them. Okay, here I can give you one hint also, that you can select your option without solving also. How you can do? If you are putting in any of the medium, focal length increases. In any of the medium, focal length will increase. So first of all, if you are shifting from air to any of the medium, focal length how to be more. Okay, focal length will increase, number one. And if medium is more than less, then positive will negative, negative will become positive. In this case, your okay, water we are keeping. Water is less than glass, less than glass. That's why positive will remain positive. But suppose I am keeping in the 5 by 2. 5 by 2 means which is more. And if it is more, then what will happen? If it is more, then okay, positive will become negative. Earlier convex given. Convex focal length is what? Positive. It will become negative. Okay, so you will select like this, that in any of the medium value will be more. If medium is dominating, medium is more, then your positive will become negative, negative will become positive. Second thing I can say here, combination of lengths. Listen. So simply you have to remember P will be equal to P1 plus P2 plus P3. Okay. If I say that okay, one lens is like this. This is the okay, two lenses I am keeping like this, or I am keeping like this. Okay, or I am keeping your okay, this way. Okay, you keep this way, then we can write here. This becomes P plus P. Here also P plus P, and here also this becomes P plus P. Means in all the cases they have the same power, same focal length. Okay, same power means here focal length. Okay, it means F1 equal to F2 equal to F3. Okay, they can say next question that lens of 20 centimeter and 25 centimeter means convex lens and concave lens 25 centimeter placed together, then focal length of combination. Then we can write here in this one, we can use the formula 1 by F equal to 1 by F1 plus 1 by F2. You can write 1 by 20 minus 1 by 25. I hope we can calculate this thing here. Yes. Okay. Now, next thing you will okay, remember the TIR. Okay, in the TIR very simple things are there and always important. That first is your denser to rarer, and angle how to be greater than theta C. Okay, and in this one we get this graph. Okay, generally we forget this graph in the TIR. Okay, like this graph is there, we get here, and here we are going to get the maximum deviation. Okay, so this is the maximum deviation here, and maximum deviation will be del max will be equal to 180 minus 2 theta C, or we can write pi minus 2 theta C. Okay, in the TIR you have to remember 180 minus 2 theta C or pi minus 2 theta C. Okay, and here sine theta C will be equal to mu R by mu D. Okay, or we can write sine theta C equal to 1 by mu if you consider the air. Okay, now sine theta okay equal to, I can write here in this one 1 by mu. Okay, now so theta C proportional to 1 by mu, 1 by mu proportional to lambda. Lambda for the red color is greater than violet color, so theta C for the red color is more than theta C for the violet. So red color will have TIR at the large angle. Red color will have TIR at the large angle. Violet color have TIR at the small angle. So if they are giving one question like this, that we are having okay like this, and this is the suppose your green color. Okay, then okay, it means if this is the green, then already some colors are inside. Which colors are inside? VIB. And which colors are outside? We can say your YOR. They can ask the same question in the prism also. We can say coming like this, and here we can write okay, this will be the your green, and here we can say this will be the inside VIB, and outside will be your okay G, then this is the Y, then this is the O, then this is your R. Okay, so this one you will remember here that your red color will be having TIR at the last. Okay, red color will be having TIR at the last. Okay, these are the things. Your mirror is similar to this one. Formula are same, so you will okay do that one. This was okay, whatever was possible we have done all the things. Okay. You keep on revising your notes. Okay, in your main notes, whatever written, you will okay at least revise okay, basic formula. I will say don't leave any chapter. At least formula for all the chapters should be known to you. Okay, because from the tough chapter they ask very easy things. Sometimes from the easy chapter they can ask slightly tough things. Okay, so you have to do all the chapters. Okay, bye. Okay, good luck for your examination. Okay, remember whatever we have done at least okay in the those chapters. Okay, most likely these things might be coming in the examination. Okay, bye.